So, how can we determine the rate of reaction? Now, whenever the word rate comes into something, it always means divide how much of something, like a mass of something or a volume of something, and divide it by time. So it could be mass in grams divided by time. It could be moles divided by time. It could be the volume of something divided by time. If you divide it by time, you've got the rate of it. So rate of reaction from a chemistry perspective is the quantity of reactant used divided by time taken, or it's the quantity of product formed divided by time taken. So rate of reaction is the speed at which a chemical reaction occurs. Now the quantity of something could be mass in grams, it could be moles, it could be volume. So that could be in decimeters cubed or centimeters cubed. Either way, it's it's an amount of something divided by time. So mass is measured in grams, volume in centimeters cubed, and rate of reaction can be grams per second, and it can also be centimeters cubed per second. It could also be decimeters cubed per second. Okay, so here's a quick question, a quick practice question. Calculate the rate of reaction when 234 centimeters cubed of gas is produced in 2 minutes. So first thing, we are measuring rate of reaction in seconds. So you've got to convert the 2 minutes to 120 seconds. Write down your formula. It's the quantity formed divided by time. In this case, the quantity formed was 234 centimeters cubed. Divide that by the time, which is 120 seconds. So we get a rate of reaction of 1.95 centimeters cubed per second. Now, particularly from an AQA perspective, it's important that you show every step of your working out. There are other examples, for example, Edexcel, where if you look at their mark schemes, they give you the mark, they give you all the marks if you get the correct answer. But in AQA, you get marks for each step. So don't just put answers. Get in the habit of doing every step. Okay, how could you use a graph to determine the rate of reaction? So if you are asked what the rate of reaction was between 0 and 60 seconds, you could use the graph to find the quantity of gas made. So volume of gas made in 60 seconds is, so here's 60 seconds. You can see the line moving upwards, where you join the line there, you move across, and you can see after 60 seconds, 48 centimeters cubed of volume of gas was made. Now, how do we work out the rate of reaction? We do quantity formed divided by time. So in this case, the quantity formed is 48 divided by the time, which in this case is 60 seconds. So the answer is 0.8. Here it is, 0.8 centimeters cubed per second. Now, how could you use a graph to determine the rate of reaction? If you asked to estimate the rate of reaction at a certain time, you would do something slightly. So here it said, what's the rate of reaction between 0 and 60? So what you're doing is, you're looking at change in time and you're looking at change in volume, which is 48, divided by change in time, which is 60. But if a question asks you what is the rate of reaction at a specific point, that's a little bit different. So if it said, for example, if you asked to estimate the rate of reaction at 40 seconds, let's do it on this one. There's 40 seconds. Now, using a ruler, you draw a tangent. Now, a tangent is a line that only crosses a circle, only touches the circle at one point. Or in this case, in a graph, the tangent is the line that touches the graph, the line at only one point. There's the one point that I've drawn that cross. Now I've zoomed in, which means the line's going to be quite thick, but hopefully you can understand what I'm trying to show you here. There we go. Now it should be touching, so it should be just a tad closer to the line. Now that you've drawn that line, the next step is to draw a triangle. So let's do it here. So when you do gradient, so now all you're doing is finding gradient of that. So gradient is the change in y divided by change in x. So really I should have drawn the y line first. So you can see in the y line, it's gone from 30 to 45, 46, 47. So change in y equals 47 divided by the change in x. So let me just get rid of this pen so I can move it down. It's gone from 20 to 50, so around 30. So 47 divided by 30, and that equals around 1.5. And we've got centimeter cubed here and seconds here. So the units will be centimeters cubed per second. And that will be just over 1.5. Let's see what it shows in the next slide. Now, this is a slightly different question. Oh, sorry, not 47. That's 17. Sorry, I completely misread that. So 17 divided by 30, so the answer is around just over 0.5, which is what we have here. So if you were asked to estimate the rate of reaction at 40 seconds, draw a tangent to the curve at 40 seconds, as they've done here. Find the change. Well, actually, the first thing you should try and find is the change in volume, the change in y, and then find the change in time to get the change in x. Divide them, and you get your rate of reaction, 0.5 centimeters cubed per second. Okay. So what are the factors that affect the rates of reaction? So we have temperature, surface area of solid reactants, catalysts, and concentration of reactants. So let's look at each one at a time. Now, in fact, before we look at this, the first thing we actually need to understand is what is a chemical reaction, or what has to happen for a chemical reaction to occur. So there's two things that have to happen for a chemical reaction to occur. One, a collision. And the second thing that has to happen is the particles have to have activation energy, meaning they have to have enough energy to react. So for example, right now, I'm sat down, I've got a piece of paper next to me to write some notes on. Why is that piece of paper not reacting with the oxygen in the air? So the oxygen and the paper are colliding, which is good, because if they didn't collide, there'd be no reaction. But even though they're colliding at this moment in time, it's not warm enough in the room that I'm sitting. I mean, it'd have to be very warm for the reaction to occur. In other words, there's not enough energy for that reaction to occur, so that my piece of paper is not burning in oxygen because we do not have activation energy. So both of these are necessary for a reaction. Not only do they have to collide, there has to be enough energy for it, activation energy. So concentration of reactants. If we, so let's use this as an example. A plus B reacts to make C plus D. So let's look at concentration of reactions. If the concentration of the reactants is increased, then there would be more particles. This means that the frequency of successful collisions would increase, and so the rate of reaction would also increase. So what we're saying here is, if we've got more of A and more of B, we've got more particles. So let's say initially we only had this many particles. If you increase the concentration, you've now got lots more. And if you've got lots more particles, we said two things have to happen. Which of these two things is more likely to happen? We're going to have more collisions. So more particles means more collisions. More collisions, if there's more collisions, we're more likely to have a greater frequency of successful collisions, which increases the rate of reaction. So you've got to answer these questions quite logically. If you increase the concentration, it means you increase the number of particles. If you increase the number of particles, you have more successful collisions, and so the rate of reaction increases. The next one is pressure. If we increase the pressure of reacting gas, so we increase the pressure, that means the particles are closer together. That means you have more successful collisions, and that increases the rate of reaction. So let's understand this really quickly. All the particles are within this much area. We increase the pressure, in other words, we decrease the space for the particles. So we have the same number of particles, but within a smaller space, there's a higher pressure. Now, if there's a higher pressure here, that means the particles are closer together. That means they're more likely to collide, as in more successful collisions. That increases the rate of reaction. So logical steps. It's all logical. It just requires time to memorize. If you understand it, you don't need to memorize it. Okay, surface area. If the surface area of a reacting solid is increased, then more reactant particles are exposed to the surface. This will mean the frequency of collisions increase and the rate of reaction increases. So let's have a look at this. Let's say you got a solid. And let's just do it as 9 particles. Actually, sorry, we'll do it as 12. Oops. Now, the only particles that are going to react are the ones on the surface. So what that means is all these that I've put a line through in red, they have to react first, and then these ones in the middle can react. But if I break this up into into smaller pieces, let's say I break this up into 4 pieces. So we had 16 atoms in that one, and the 4 atoms in the middle were not available to react until the ones on the outside reacted. But now I've broken this up into 4 atoms each. Now, every single one can react. So when we say increase the surface area, it means we're breaking it into smaller pieces. We're making more of it available to react. These ones here in the middle are not available to react until the ones on the outside have. When you've made the surface area smaller, everything is available to react. So that means you have more successful collisions, you increase the frequency of successful collisions, and the rate of reaction increases. Now the next one is temperature. If we increase the temperature, the rate of reaction would increase also. But why would it increase? Because now, two things. The particles have got more kinetic energy. In other words, more particles have activation energy. So you know how we've got oxygen hitting my piece of paper and nothing happens because there's no activation energy? In this case, we have more particles with activation energy. The other thing is if they've got more kinetic energy, they're going to move around faster. They're moving around faster, they're more likely to collide. So if we increase the temperature, we're increasing the speed at which the particles are moving, and we are also increasing the energy within each particle. So we are changing things so that more particles have activation energy. So that means we're going to have more successful collisions, and there's going to be an increase in the rate of reaction. Okay, the presence of catalysts. Now, catalyst speeds up a reaction, so it increases the rate of reaction, but it doesn't become part of the reaction. Now, in a chemical reaction, what a catalyst does, it provides an alternative pathway that has a lower activation energy than the uncatalyzed reaction. What that means is less energy is needed to react. So that means more of the collisions are successful. Again, going back to my piece of paper, the collisions are occurring, but they're not occurring with activation energy. When you add a catalyst, more of the collisions occurring are successful. So the frequency of collisions does not change, but the number of collisions with sufficient energy increases, which means the rate of reaction increases. So it's important to memorize this bit here. Actually, the whole thing. Again, this is the kind of thing, when you look at past paper questions, hopefully you've all doing lots and lots of past papers, but the more you do, you're going to see the same kind of thing over and over again. So, how can we use equipment? How can we use equipment to investigate the effect different factors have on the rate of reaction? So again, these are important practicals, and it's important to be aware of how each practical works. So if gas is measured, so in this reaction, what we've got here is most likely a metal or metal oxide or metal carbonate, and then we've added acid. And the acid and the metal carbonate are reacting with each other to make hydrogen. And that hydrogen gas goes here. Now, if it was a carbonate, then it makes carbon dioxide. So it's not really going to be a metal oxide because it only makes water, you won't get gas. So it would have to be just the metal or the metal carbonate. That is then trapped here in the gas syringe. Now, if a gas is produced, we can measure the volume of gas produced at fixed time intervals. It means at 0 seconds, you write down the volume of gas produced. After 30 seconds, you write down the volume of gas produced. So every 30 seconds, you're writing down the volume of gas produced. Alternatively, you could measure the fall in mass in a fixed period. So if you get the same conical flask, because the gas is produced and is released, when you put this on a mass span balance, the mass decreases over time. So it shows that a reaction is occurring. Another thing we can do is we can use a white tile with a black cross on. We can allow this reaction to occur, and as a precipitate is made, it starts to, well, it becomes more difficult to see the cross. And we time how long it takes for the cross to disappear. Now, one thing we would do when we're doing this is, for example, in this experiment, we might use different concentrations of acid. Same in this experiment, we might use different concentrations of acid. And we might want to see what the impact of changing concentration has on the rate of reaction. Because once we've got time, and here we've got we've got the volume, uh, we can draw our graph and we can calculate the reaction. Then we can do the whole thing again at different concentration, and draw that graph on the same table showing the different rate of reaction. Same thing here. We can try different concentrations. Another thing we can change is the temperature. We could do this whole experiment at 10 degrees. Then we could do it at 20 degrees, 30 degrees, 40 degrees, and see what impact that increase in temperature has. Again, we will draw graphs for each temperature and then do a comparison. So a method to investigate how changes in concentration affect the rates of reaction by measuring the volume of gas produced. This is a good way of answering any question that's linked to uh, investigations. Number one, always outline the method. So start by outlining the method. Within that method, add your dependent variables. Within your method, add your independent variable. So apologies, that's been missed out here. Then your dependent variable and your control variables, and have your step-by-step method. And you should add your health and safety precautions as part of your method. But usually, if you have a 6-mark question, for example, on questions like this, then it will state what it wants in a 6-mark question. So it might want the method. It might want you to outline how the rate of reaction can be determined. Now, if you determine the rate of reaction, you would still do all of this, but you'd finish with you draw the graph, and because you measure the time and you measure the change in mass, and then by doing that, by putting the change in mass or volume here, by the time here, you can work out the rate of reaction. So here it's just giving you a method. Put 50 centimeters cubed of sodium thiosulfate solution into a conical flask. Put the container on a cross drawn on a piece of paper. Measure the time it takes for the cross to disappear. Make sure that your concentration and volume of sodium thiosulfate stays the same. The volume of acid stays the same. The temperature of the reactant stays the same. And then you repeat the whole process using a different concentration of sodium thiosulfate and see what difference that makes. So you can change this, you could change this and see what impact that has. Okay, collision theory. Now, this is something which we've already covered. This is the one thing I disagree with in the order of AQA, is that collision theory should come first. Because what collision theory is a theory that states that chemical reactions occur when reacting particles collide with enough energy. And when we say enough energy, what do we mean? Activation energy. So in other words, what I went through before I started the other topic, before I went through rates of reaction just a few minutes ago. So activation energy is the minimum energy required for a reaction to occur. So what is collision theory? Increasing the concentration of reactants, pressure, surface area, increases the frequency of collisions, and so it increases the rate of reaction. Increasing the temperature increases the frequency of collisions, but it also makes the collisions more energetic. In other words, they have more energy, they have activation energy. Catalysts. A catalyst is a substance that lowers the activation energy of a chemical reaction but are not used up themselves. Different reactions need different catalysts. Enzymes are biological catalysts, so they're the enzymes that we're using. digestion. Now, a catalyst increases the rate of reaction by providing a different pathway for the reaction that has a lower activation energy. So look, we've got a reaction happening here. It's an exothermic reaction because the reactants have got less energy. Sorry, this is an endothermic reaction, sorry, because the reactants have got less energy and the products have got more. So now usually it requires this much energy for the activation to occur, for the reactions to occur. But with an enzyme, you've got an alternative path provided, so you need this much energy for the reaction to occur. I would advise you memorize this. It was covered for paper 1, but I advise you memorize this now. Okay, Le Chatelier's principles. So we're now looking at reversible reactions. Now, just so you're aware, you can probably hear I've got a little bit of a sore throat. So if I go quiet for 10 seconds, it just means I'm having a hot drink. I've got a hot drink with me and it just soothes my throat. It helps me talk. My throat is much, much better than what it was a few days. In fact, we were, to some extent, we were concerned and we were thinking how we can fulfill what we promised to everyone with the way I was feeling a few days ago. But since then, my sore throat's gone. My voice is coming back again. Okay, so what are reversible reactions? So what we're saying here is when A and B react, they make C and D. But when C and D react, they make A and B. So it means the reaction is reversible. It's going in both directions. The direction of reversible reactions can be changed by changing the conditions. So what Le Chatelier's principles look at is when you've got a reversible reaction, how can we manipulate it so we make more of the product? Because the issue here is you've got lots and lots of A and B to start with. You've got lots and lots of A and B to start with. A and B start reacting and they start making C and D, which is brilliant. A company that's making C and D, so let's use this as an example. A company heats up ammonium chloride, they make ammonia and hydrogen chloride. They want the ammonia so they can sell it. Ammonia is used in lots and lots of different reactions. But as they're trying to remove it, the ammonia starts reacting with hydrogen chloride to make more ammonium chloride. Now, as a business owner, that's going to be a little bit annoying because the product that you want doesn't stay. So this is where Le Chatelier's principles manipulate reactions. Is the changes in the reaction that enable you to make more of one or the other. So a reversible reaction is, as I just said, a chemical reaction in which the products of the reaction can react to make the original reactants. So it goes in both directions. So here we've got an example of a reversible reaction. We've got hydrated copper sulfate. Hydrated copper sulfate means it's full of water. In other words, it's copper sulfate solution. So this is possibly an experiment you did at school. Copper sulfate, when it's added to water, has a blue color. The forward reaction is endothermic, meaning it needs to take energy in. When it takes energy in, it separates the water part from the copper sulfate, leaving us with anhydrous copper sulfate, which just means dehydrated, as in where the water has been removed and water. Now, anhydrous copper sulfate, if you add water to it, it's exothermic, it releases heat energy. And it goes back to being this blue hydrated copper sulfate. The same amount of energy is transferred in each case. So the amount of energy that is taken in during endothermic reaction is the amount of energy that we release during the exothermic reaction. But again, we have the problem that it's a reversible reaction and the anhydrous copper sulfate and water react to make hydrated copper sulfate. That breaks apart to make anhydrous copper sulfate and water, which react with each other to make the hydrated copper sulfate. So we don't get to a point where we have 100% of the product. So what is equilibrium? Equilibrium is only achieved when a reversible reaction occurs in apparatus, which prevents escape of reactants and products. So it means when you're doing the reaction, you put a lid on top of it. And you can only reach dynamic equilibrium or have an equilibrium if you put a lid on top and none of the reactants are lost. So it has to be a closed system. So equilibrium is only achieved when the reversible reaction occurs in apparatus, which prevents the escape of reacting the product. In other words, it has to be a closed system. Now, dynamic equilibrium is a point reached when the forward and the reverse reactions in a reversible reaction occur at exactly the same time. So, of course, when you have more reactants to start with, so the reactants start reacting with each other to start to make the product. But then at the same time, the product is reacting to make more reactants. So it's happening in both directions until we get to a point where the rate of reaction going this way is exactly as the rate of reaction going that way. Now, if the amount of product being made is the same as the amount of reactant being made, what does that mean? It means we get to a point where we can't increase one or the other. We have reached a point where whatever we've got, so let's say we've got 40% reactant and we've got 60% product. When you reach equilibrium, because the rate of reaction, the forward and the back is the same, we don't increase in reactant, we don't increase in product. That's the maximum product we're going to make. So dynamic equilibrium is a little bit like an escalator that's going downwards and a child that's trying to run up the escalator. And it's possibly something we've all tried when we were younger. But what happens at a certain point is a person's running upwards, the escalator is moving downwards, but what happens? The person is no longer able to move beyond a certain point. So you see some children running as hard as they can, but they're stuck on, for example, the first, second, the fourth step. But they're still moving. So they're still moving upwards, the escalator is still moving downwards, but that child isn't moving from the spot. That's dynamic equilibrium. So that's what we mean here. The hydrated copper sulfate is making these two things, and anhydrous copper sulfate and water is making the hydrated copper sulfate, but it's happening at the same rate. So if I've got 40% of this and I've got 60% of this, that's it. That's the max we're going to get to. Unless we change the temperature, unless we change the concentration of something. Okay, so what happens? What happens if conditions? What happens to conditions when a reaction? What happens if conditions when a reaction is in equilibrium change? The relative amounts of all the reactants and products at equilibrium depend on the conditions of the reaction. If a system's at equilibrium and a change is made to any of the conditions, then the system responds to counteract the change. So if I've got A plus B makes C plus D, if this is an endothermic reaction, and we'll go through the more detail, if I increase the temperature, that pushes my equilibrium towards C and D, meaning I start to make more product. So let's say initially it was 60% reactant and 40% product, but I increased the temperature and now I'm starting to make more of the product. So it might go from 60% to now being 50% of each being made. But what will happen is the equilibrium. So it says here, if a system is at equilibrium and a change is made to any of the conditions, then the system responds to counteract the change. So this is what the system's done to counteract the change. The increase in temperature has pushed the equilibrium towards C and D until we get to a point where the rate of reaction becomes the same in both directions. And that's why we end up pausing at a certain percentage again. But at least for a company that's dealing with this, they're making more of the product. Now, Le Chatelier's principles is a principle that states if a change is made to a system, the equilibrium will shift to counteract that change. So, a principle, Le Chatelier's principle is a principle that states if a change is made to a system, the equilibrium will shift to counteract the change. So when we increase the temperature in this reaction, what happened? The equilibrium shifted to the right, shifted towards the product end. And that was to counteract the change. Okay, so the next few slides, we'll just go through some of the different things that we can change. Now, if anyone wants me to repeat anything, as some of you have been messaging, just keep messaging. And then I will go through whatever needs to be gone through as many times as you require. So if the concentration of a reactant, if the concentration of a reactant is increased, more product will be formed until the equilibrium is reached again. So now we're initially looking at change in concentration. So if you increase A, or if you increase B, the equilibrium shifts to the right. So we start to get more of C and D until we reach equilibrium again. Now, one of the best ways to learn how to answer these questions are through past paper practice. I know I probably sound like a broken record now, but understanding and past paper practice, this is the way to get your grade 9s. Or if you're doing foundation, it's the way to get your grade 5. So if the concentration, and with what you'll see in the past paper practice is that, what you'll see in the past paper practice is that, sorry, excuse me. Yeah, what you'll see in the past paper practice is that you'll see what the examiner is looking for, the wording. And when you see one question, you'll see that the mark scheme is almost identical in every single question. So if the concentration of one of the reactants or products is changed, the system is no longer at equilibrium. So the concentration of all the substances will change until equilibrium is reached again. So in this case, if we increase the concentration of A and B, the system is no longer at equilibrium. And the concentration of C and D will start increasing until equilibrium is reached again. So if the concentration of a reactant is increased, we get more product, get more of C and D. Alternatively, if we decrease C and D, make them a smaller amount, more reactants will react until equilibrium is reached again. Because what we're saying is we've decreased C and D. We want more of C and D. So we increase the reactions in A and B, so that we end up with more C and D, so it goes back to normal. Okay, now if the temperature of a system at equilibrium is increased, the relative amount of products at equilibrium increases for an endothermic reaction. So look, if we increase the temperature, it always goes in the endothermic direction. So in this case, the forward reaction is endothermic. So if we increase the temperature, we get more anhydrous copper sulfate and more water. The backward reaction, the reaction going in the left direction, is exothermic. So if we increase the temperature, we get less hydrated copper sulfate solution. Now, that's because when we increase the temperature, but actually, let's look at endothermic. What does endothermic mean? If you've got, for example, something that needs to decompose, break apart, it needs energy to break the bonds. So it takes in the energy to break the bonds. That's endothermic. So the surroundings get cooler. So when you have an endothermic reaction, the surroundings get colder. Now, if I warm up the surroundings, what am I providing? I'm providing more energy to go inside. I'm providing more energy to go inside to break the bonds. So an increase in temperature supports an endothermic reaction. Now you don't need, for the exam, you don't need to explain it in that much detail. However, I'm explaining it in that much detail so as to help you understand it better. Because I want you to remember that if you have the better your understanding, the less you will have to memorize. So if the temperature of a system is at equilibrium, the temperature of a system at equilibrium is decreased, then the relative amount of products at equilibrium decrease for an endothermic reaction. So here the forward reaction is endothermic. That means we're going to make less anhydrous copper sulfate and less water if you decrease the temperature. If you increase the temperature, it goes in if you decrease the temperature, it goes in the exothermic direction. So that means you get more this. So an increase in temperature is endothermic, and a decrease in temperature is exothermic. It prefers the exothermic direction. So the equilibrium shifts. If you increase the temperature, the equilibrium shifts in the endothermic direction. If you decrease the temperature, it shifts in the exothermic direction. Now, another thing to keep in mind here is that not all reactions are endothermic in the forward direction. Not all reactions are exothermic in the opposite direction. Some will be exo in this direction, and some will be endo in the backward direction. Now, changing pressure. This is something that needs to be memorized and just keep it in mind. Let's use the Haber process as an example. So nitrogen plus 3 hydrogens, reversible reaction, gives us 2 NH3. Now, a decrease in pressure caused the equilibrium position to shift towards a side with a larger number of molecules. An increase in pressure caused the equilibrium position to shift towards the side with a smaller number of molecules. So on this side here, we've got 1 nitrogen, 3 hydrogens, we've got 4 molecules. In our product side, we only have 2 molecules. So when you increase the pressure, it says it caused the equilibrium position to shift towards the side with smaller number of molecules, which means the equilibrium shifts in this direction. So we end up making more. So an increase in pressure would mean more NH3 is made. So in chemistry topic 7, 7.1 is all 7.1 is linked to combined and triple. 7.2 and 3 is triple. So after around slide 20 onwards, will be triple only. So those doing combined can take a bit of an extended break and then join us for the final physics session at that point. So what is crude oil? Crude oil is a mixture of hydrocarbons found in rocks. It is the remains of ancient biomass that was buried in the mud. And the hydrocarbons are molecules made up of hydrogen and carbon only. So if this ever comes up as a question, which it does, crude oil is a mixture of hydrocarbons. And the word hydrocarbon, if it comes up, if it said, what is a hydrocarbon in an exam, you say it's a molecule made of hydrogen and carbon. That's your first mark. Only is the second mark. So crude oil is a mixture of hydrocarbons, as in something made of hydrogen and carbon, only. That's found within the rocks, under the rocks. And it's animals and plants that died millions of years ago, and because they've slowly decayed, because of the circumstance under which they were buried into the mud, they've eventually turned into a fossil fuel. So alkanes. Now, alkanes and alkenes are two of the things that are found within crude oil. Different types of alkanes, different types of alkenes. Alkanes is linked to combined and alkenes is linked to triple. So what are alkanes? Alkanes are a group of molecules with the general formula CnH2n plus 2. What that means is if you've got, let's go with one carbon. So what we would do is replace the N with 1. C1H. Now that 2n plus 2 means 2 times 1 plus 2, which is 4. So when there's only one carbon, we get CH4, which is correct. One carbon, 4 hydrogen, CH4. Let's try it for propane for 3 carbons. So 1, 2, 3. So we've got C3H, 2 times 3 plus 2. 2 times 3 is 6, plus 2 is 8. So propane should be C3H8. And that's correct. We've got 3 carbons and we've got 1, 2, 3, 4, 5, 6, 7, 8. So you do need to know this. Methane, meth means 1 carbon. Eth means 2 carbons. Prop means 3 carbons. Bute means 4 carbons. The ane part means that all the bonds are saturated, meaning you only have single bonds. So in alkanes, you only have single bonds. And the whole family of alkanes follow this general formula. So how do we know something is an alkane? It follows that general formula, CnH2n plus 2. Or you could say alkanes always have, in terms of the number of hydrogens, it's always twice the number of carbons plus 2. So we have methane, which is CH4, ethane, which is C2H6, propane, which is C3H8, and butane, which is C4H10. And you should know how to draw them. So one thing you've got to remember for this is if you're told, for example, to draw propane and it's got 3 carbons, the first thing you do is draw your 3 carbons. 1, 2, 3. Each carbon can have 4 bonds. So this first carbon already has 1 bond here. So I'm going to add number 2, number 3, and number 4. The carbon in the middle already has 2 bonds. So we're going to add number 3 and number 4. The carbon at the end has already got one bond with the other carbon, so it's got two second, third, and fourth bond available as well. And don't forget, alkanes are hydrocarbons, meaning they're only made of hydrogen and carbon. So there's your three carbons. Every other bond is going to be hydrogen. So now let's do a slightly more complicated one. Not complicated, but just one that's not in front of us. Let's try um, pentane. Pentane, so you might get a question that says it's got five carbons, draw the diagram for it. So what you would do is initially draw your five carbons. One, two, three, four, five. Then add in all the additional bonds they can have. So his first carbon, one, two, three, four. That carbon's already got two, so we can have two more. This carbon has already got two bonds, so there's second, the third, and the fourth. This carbon has also already got two bonds. So one, two, three, and four. And that carbon at the end has got one bond, so one, two, three. Then all you're doing is adding in your hydrogens. So we're adding one, two, three, four, five, six, seven, eight, 9, 10, 11, 12. So we've got C5, 8, 12. Does that fit with the general formula? We've got five carbons, double it plus 2. So 5 times 2 is 10, plus 2 is 12. So yep, that's correct. So know how to draw them. Okay, fractional distillation. Fractional distillation is a way of separating molecules with a similar number of carbon atoms into fractions. The fractions can be processed to make fuels and feedstock for the petrochemical industry. So what we're saying here is that crude oil, like we said before, is a mixture. What fractional distillation does, and we say it's a mixture, we mean you've got some carbon, you've got some molecules in there that have got 100 carbon long chains. The smallest one might only have one carbon, for example, CH4. You might have some that have got 80 carbons in a chain, some with 60, some with 5, like pentane, the one that we just drew. So all of that, they're all hydrocarbons. They're all within crude oil as a mixture. Now, as a mixture, they've got no use. Separately, each one has a separate individual use. So what fractional distillation does is it separates them all. Now, the simple distillation is, for example, in here I've got two liquids mixed up, alcohol and water. Now, if I heat this up to about 70 degrees, the ethanol will evaporate. When it goes to this middle part here, it will condense because there's a condenser attached to it, and it comes out the other end. So we have ethanol here, and the original substance, what we're left with is water. So we've separated the water and the ethanol. Fractional distillation is a bit more complicated because you've got so many different things that need to be separated. So many of the fuels on which we depend for our modern lifestyle, such as petrol, diesel, oil, kerosene, heavy fuel oil, liquefied petroleum gases, are all produced from crude oil. Um, and many of the things that we use on a day-to-day basis, like solvents, lubricants, polymers, detergents, and a lot of natural and synthetic carbon compounds all come from the separation of crude oil. They all come from crude oil. So separating them into all these different fractions is very important because it ensures that we can cook on our stoves. It allows our cars to move. It allows our planes to move, our lorries and vans, boats. It makes the surface, the bitumen that's released, it makes the roads. So all of this stuff is important. This process is important. So this is the actual process now. The column is hotter at the bottom and it's cooler at the top. The crude oil, so the crude oil enters from here at over 300 degrees, so it's heated and vaporized. In other words, it's turned into a gas. So the temperature is taken so high that everything inside it turns to a gas, except bitumen, which is still a liquid. And because it's still a liquid, it goes straight to the bottom and it's siphoned off. Now, as it's a gas, the gas particles start to rise. They enter the column, so this is the column. They enter and they start rising. Now, as the vapors rise, they cool and condense at different levels. So the really long chained ones, they condense at a higher temperature. So they'll hit this surface here, turn to a liquid, and they'll be siphoned off. Diesel will collect here and will be siphoned off. Naphtha, it will collect at around 120 degrees and it'll be siphoned off. So small molecules condense further up, while larger molecules condense further down. Larger molecules, so let's have a look. That's ethene. Now that ethene molecule, for it to attach to another ethene molecule, it'll have intermolecular bonds. They're weak intermolecular bonds, weak van der Waals or weak intermolecular bonds. Now if we look at pentane. Now, relative to this whole thing, pentane is not very big, but just the same we're drawing 50 or 100 carbon atoms. Now, that pentane molecule there, for it to attach to another pentane molecule, it'll form weak intermolecular bonds. But the larger molecule will produce stronger or more weak intermolecular bonds. So that means ethene has a lower melting and boiling point and a lower condensing point. So it turns back into a liquid at a lower temperature. So this will rise all the way to the top, higher up towards the top. Pentane, on the other hand, will rise up to around here. So C2H, so the gas, ethene will rise up to about there. And pentane, C5H12, will rise up to about here. So the more carbons we add in the chain, the stronger the covalent bonds, the more, not covalent bonds, sorry, the intermolecular bonds between the molecules. So more and more energy will need to separate them. So they condense at higher temperatures. So these are key words that we've already covered. Now, properties of alkanes, another very common question and one that we should know. So CH4, the smaller the molecule, so you can see here, the molecules are getting bigger as they go down. The smaller molecules are more flammable than the larger molecules, meaning the smaller molecules burn more easily. The smaller molecules have got lower boiling points. As the molecules get bigger and bigger, the boiling points become higher. The small molecules are less viscous. Viscous is the ability for it to flow. So if something is more viscous, it doesn't flow as well. So lack of ability to flow, I suppose. There's a definition just here. Viscosity, the larger molecules are more, actually that doesn't give you a definition. So less viscous means it flows. The more viscous means it doesn't flow as much. So for example, honey is viscous. If I got some honey, took the lid off, turned the jar upside down, the honey would flow out slowly. Whereas if I got a bottle of water, I opened the lid, turned it upside down, it would come out straight away. So smaller molecules are less viscous, they flow more easily. Larger molecules flow more slowly, they're more viscous. Again, another common question, the combustion of alkanes. So methane and oxygen react to make carbon dioxide plus water. Because what's methane actually made of? It's made of hydrogen and carbon. So what do two hydrogens make when they react with oxygen? This is not balanced, but it makes H2O. What's carbon going to make when it reacts with oxygen? CO2. So the only thing an alkane can combust into, combustion means a reaction with oxygen. So combustion of alkane can only make water and carbon dioxide and nothing else. And when this reaction happens, energy is released during complete combustion. So what we're showing here is complete combustion. Because incomplete, we will look at in a second. That makes something completely different. Not completely, but it makes additional things like carbon monoxide and carbon. The carbon and hydrogen in the fuel is oxidized. When we say oxidized, we usually mean loss of electrons. Here, we mean adding an oxygen. When you add oxygen to something, that's also called oxidized. It's oxidized to make carbon dioxide and water. So here's our word equations, which usually come in foundation, and here's our symbol equations. So here, that's incorrect. So can you give me the correct symbol equation for ethane? So I'm going to give you 1 minute to give me the correct symbol equation for ethane. Okay, thank you to those that gave me answers. Let's quickly go through this. So ethane is C2H6, and to it we're adding oxygen. So it can only have two products, which is CO2 plus H2O. So now we've got two carbons here. So that means we're going to have two carbon dioxides. We've got 6 hydrogens. So that means we're going to have 3 H2O because 3 times 2 is 6. Then all we're doing is looking at the number of oxygens. So 2 carbon dioxides gives us 4 oxygens. 3 waters gives us 3 oxygens. So altogether we've got 7 oxygens. That means we have 3.5 O2. Now, you can actually write the answer here as 3.5 O2, or you can just double everything. So we can either write this as 3.5 oxygens. Now that's balanced. It's okay to write things as halves. The other option, that we have is we just double everything. So that means we do this. 2 C2H6 plus 7 oxygen gives us 4 carbon dioxide plus 6 H2O. And that's absolutely fine. We can do that without a problem. So I hope that makes sense. Let's continue. Okay, cracking and alkenes. So what is cracking? So large hydrocarbons tend to not be very useful. So cracking is taking a hydrocarbon and breaking it down. That's what I mean by cracked. So hydrocarbons can be broken down, cracked, to produce smaller, more useful molecules. So cracking is taking a large hydrocarbon and breaking it into smaller, taking a less useful large hydrocarbon and breaking it, cracking it into smaller, more useful molecules. This does come up as 1 or 2 mark questions sometimes, so please do memorize what cracking is. So when you crack a large hydrocarbon, you make smaller, more useful molecules. So there's two types of cracking, and you need to know both. Catalytic cracking is high temperature and a catalyst, and steam cracking is a high temperature and steam. I have seen this question once where it comes up every once in a while where it asks you for conditions for the cracking, and you can put either high temperature and catalyst, or you can put high temperature and steam. Now, whenever we do cracking, we make two things. We make a small alkane and we also make an alkene. Now, small alkane is useful as a fuel, and the alkene can be used to produce polymers. So it can also be a starting material for the production of many other chemicals. Now let's have a quick look at C10H22. And it has been turned into C4H10. Now C4H10 is an alkane. Now, how many carbons do we have left? Now, in this question, they might ask you to write down the name of the molecule that's remaining. So what do we have left? From the 10 carbons we started with, we've used 4 up in the butane. So we've got C6 left. And hydrogens, we have 12 hydrogens left. Now, notice over here, it's an alkane because the number of carbons have been doubled plus 2. So 4 times 2 is 8, plus 2 is 10. Here, however, the number of hydrogens double the number of alkane, the number of carbons. Number of hydrogens is double the number of carbons. So this is an alkene. So it's impossible to make just alkanes. It always makes an alkane and an alkene. Okay, so how can we test for alkenes? Alkenes are more reactive than alkanes. They react with bromine water and turn it colorless. So this is used as a test for alkenes. Now, I just want to very quickly explain why this happens, because it's not always understood. This is more A level, but it's important just to understand it. If you have alkene, you've got your carbon-carbon double bond. Now along comes bromine. Bromine's inside the water at this point. What will actually happen is this: the bromine, without going into too much detail, the bromine causes a break in that bond there. And then one bromine, so let me just draw the bromines here. That causes a break in the bond between the bromines as well. So now we've got 2 separate bromines. One bromine now attaches here, because don't forget, carbon can have 4 bonds. So now that double bond is broken, that carbon is now able to bond to the bromine. So what that does is, it takes the bromine out of the water. So alkenes turn the bromine water colorless because it takes the bromine out of the water. In other words, it takes away the orangey red color. Now in an alkane looks like this. Each carbon is already bonded to 4. So when the bromine comes along, there's no space for it. In what I just showed you here, in an alkene, when the bromine comes along, the double bond breaks. So now each carbon has an additional bond where the bromine can attach. It doesn't matter where the bromine attaches, as long as one bromine attaches to this carbon and one attaches to this carbon. So it takes the bromine out of the water, makes it colorless. Okay, this is what I've already shown you. The only thing is, it should just be small alkane made and 2 small alkenes made, because that is an alkene. It should be hexene. C6H12 is a alkene. Okay, so this point onwards, it is triple only. So if anyone's doing triple, we will be taking a break at 1 o'clock. So at 1:05, we'll be starting our physics. So if anyone is doing combined, you can stay logged in if you want. Entirely up to you. Okay, so 7.21, structure and formula of alkenes. This point to the end of topic 7 is triple only. So what are alkenes? Hydrocarbons with double carbon-carbon bonds. They have general formula CnH2n. So what we're saying here is in alkenes you have double bond. In alkanes you only have single bonds. In alkene you have a double bond. So double bond is made of only carbon or hydrogen. It follows this general formula, CnH2n, meaning there's always twice as many hydrogens compared to carbon. So double bond is made of only carbon and hydrogen. Double bond is between carbons, by the way. And general formula, the hydrogens are always twice as much as the carbon. Now, why can we not have methane? Because here it shows ethene, propene, butene, pentene, but why no methane? That's because there's only one carbon, so it can't make a double bond with anything. Now, notice here that they've put the double bond here. You can also put the double bond here. In butene, you could put the double bond here or you could put it here, but only one double bond goes in each one. In pentene, you could have put the double bond here, here, or here. So the double bond can go anywhere within the molecule. So alkenes are hydrocarbons with the functional group carbon-carbon double bond. The reactions of alkenes is determined by the functional group. So the functional group means the thing that sets it apart from other types of chemicals. So all alkenes have this carbon-carbon double bond, and that's it. They don't have any additional features other than the fact they have carbon and hydrogen only. They are hydrocarbons. And it's that carbon-carbon double bond that makes them reactive. So the reactions of alkene is determined by the functional group. Usually it's the functional group that is involved in the reaction. So let's look at some reactions of alkenes. What is the reaction with alkenes and oxygen? Alkenes react with oxygen in combustion, reaction in the same way as other hydrocarbons. So alkenes react with oxygen in combustion reactions in the same way as other hydrocarbons. So the alkene plus oxygen makes carbon dioxide and water. Now, the issue with alkenes is they have a tendency to burn with a smoky flame because they are more likely to have incomplete combustion. Now, during incomplete combustion, you don't just get carbon dioxide and water. Because there's a lack of oxygen, you also end up with carbon monoxide, and you also sometimes end up with carbon particulates or soot, which is just carbon. So if anyone's read about the Industrial Revolution, there's a lot of fossil fuels being burnt at that time. And in cities like Manchester and around the United Kingdom, wherever they had factories, the trees started to change color. So when particularly the silver birch trees, so trees that are silver have a silverish white bark, started to have a darker black color because the carbon soot started to attach themselves to the trees. Okay, what happens when alkenes react with hydrogen, water, and halogens? So this is what I was explaining to you before, but now we're going to look at it with hydrogen, we're going to look at it with water, and we're going to look at it with halogens. When the alkenes react with carbon-carbon double bonds, when alkenes react, the carbon-carbon double bond breaks and becomes single carbon bond. So look what happens. Let's bring along hydrogen. If this double bond breaks, we've now got two extra bonds left. Don't forget, carbon has got 4 bonds. So carbon's got, let's quickly highlight how many bonds it has. It's still got this bond, and this bond. And now I've added a 4th bond there. This carbon has got this bond in the middle, 2, 3, and the 4th one that I just added. Now what will happen is this hydrogen will attach here, and this hydrogen will attach here. So we have just converted C2H4, we added hydrogen, and we finished up with C2H6. So we turned ethane into ethene. Sorry, we turned ethene into ethane. We call this hydrogenation because we've added hydrogen. Okay, now let's look at another example. Let's look at water. Now, water, if you think back to acids, water is actually a H plus group attached to a OH minus group. But in terms of covalent bonds, we usually draw it like this. Now, when they split, it splits into H and OH. So again, we're hydrating the ethene here. We're hydrating, we're adding water to it. So when it breaks apart, the OH minus attaches here and the H attaches here. Or the other way around, it doesn't really make a difference. In other words, we have just made ethanol, alcohol. So now we've got C2, 1, 2, 3, 4, 5. Got 1, 2, 3, 4, 5 hydrogens, H5, and OH we keep as one thing, so we don't add that as H. That's one functional group. So we've taken ethene and converted it into ethanol. So ethene becomes ethanol. Okay, now let's do the halogen one. The halogen one actually I've already shown you when I was showing you bromine. The only difference is it could be 2 fluorines. It could be 2 chlorines, 2 bromines like we just showed. Okay, I hope that makes sense. So alkene and hydrogen makes an alkane. This is an addition reaction. Alkene plus water makes an alcohol, which is also an addition reaction. Alkene plus halogen makes halogenoalkanes. So, so I'll give you an example. The one that we drew before, but let's do it here. Let's do chlorine. So we break the double bond. One chlorine attaches here. One chlorine attaches here. So we'd call this chloroethane. Well, this would be dichloroethane because it's 2 chlorines. So it would be chloroethane. Okay, alcohol groups. A chemical with the functional group OH. So this is the part that's reactive, and this makes it distinctive compared to other compounds. You just have the OH group. So methanol, meth means 1 carbon. When we say anol, it means OH. And now all we've got to do is go back to that carbon and make sure it's got 4 bonds. So it's got 1 already, 2, 3, 4. I'm just filling the hydrogens. Let's try propanol. So we've got one, prop means three carbons, so we draw our three carbons. It says anol, so we add our OH. Then we're just filling the rest with hydrogens. So don't forget this carbon can have four hydrogens, so it's already got one. I think it can have four bonds, sorry, so it's got one bond already. 2, 3, and 4. This carbon can have four bonds as well, so it's already got two. There's 3 and 4. This one's already got two, so there's 3 and 4. So now we've got C3, 1, 2, 3, 4, 5, 6, 7, H7, and OH. Good. Okay, so a really good question is the rule multiply by 2 and add 1. So what you can do is, yeah, with the carbon, there's no general formula for alcohol, but what you would do is, you're right, you double the carbon and add 1. So that gives you 3 hydrogens and add an OH at the end. So if we were doing C5, double it, add 1. So double 5 is 10, plus 1 is 11, and add the OH at the end. So that does work, but there's no actual general rule. Okay. Now, if alcohol reacts with sodium, it makes salt plus hydrogen. Alcohol plus oxygen makes alcohol plus oxygen makes carbon dioxide plus water, because alcohol is made up of carbon, hydrogen, and oxygen. An alcohol an oxidizing agent, meaning you're just adding oxygen to it without burning it, makes carboxylic acid and water. So let's have a look at some examples. Let's specifically look at when ethanol reacts with oxygen. Apologies, my throat's still a little bit bad. Okay, so methanol plus oxygen gives us carbon dioxide plus water. So we've got methanol, CH3OH, plus oxygen. The easiest way to do this is first look at your carbons. Now we've only got one carbon, so we're only going to have one carbon dioxide. Then look at your hydrogens. We've got 3 and 4 hydrogens. 4 hydrogens will give us 2, 2H2O. It'll give us 2 waters. Now add the oxygens on the right hand side, and we have got 2, 4. On the left hand side, we don't. So this is not balanced at the moment. So that would need balancing. Which I'm going to ask you guys to very quickly have a go at. So can you try and balance methanol plus oxygen? So did anyone manage to do it? It's actually, it's quite a tough one to be honest. Um, so if you didn't manage, it's not a problem. So you put a 2 there because that temporarily balances the oxygens. But now you've got 2 carbons. So we put a 2 here. And now we've got 8 hydrogens. So you put, instead of a 2, you turn that to a 4. So that means now we have got on this side 8 oxygens altogether. Because 2 times 2 in the carbon dioxide and 4 times 1. So we've got 8 oxygens. On the left hand side, we've got 2 oxygens already here and we've got O2. So 2 are already done. We need 6 more oxygens. So we put a 3 here. Okay, so C2H5 plus 3O2, that's already balanced. And we've got some more balanced examples here. So what happens when alcohols react with oxygen? So solutions of ethanol are made when sugar solutions are fermented using yeast. So when yeast feeds off sugar, it uses that sugar for respiration. So you can do fermentation with oxygen and you can do it without oxygen. Now, if it's done without oxygen, so it's done anaerobically, then that produces carbon dioxide and it produces alcohol, ethanol. And that takes place between 25 to 35 degrees. Otherwise, the enzymes in yeast, which is a living organism, die. So yeast, sugar and water, so sugary water and yeast eventually makes ethanol, as long as it is anaerobically respiring, meaning you've got to put it in a sealed, it has to be in a sealed container. And it's between 25 and 30 degrees, so the right temperature for for the enzymes to work best at. Around 15% alcohol, when the ethanol is about 15%, that kills off the yeast. So the yeast are poisoned by the ethanol. The same way we would be poisoned by our excrement or urine. So, uses of ethanol or alcohols. So, ethanol is an alcoholic drink, such as wine and beer. It's also a solvent in marker pens, medicines, perfumes, deodorants, meaning, there are certain things that won't dissolve in water. So, they get a small amount of ethanol and dissolve it into the ethanol instead, and then mix that in. It's also used to make fuels. Okay, carboxylic acids. Now, let's really quickly, I'm going to go back for a second. It said here alcohol plus oxidizing agent. So let's use a simple alcohol. Alcohol plus oxidizing agent makes carboxylic acid. So let's use, um, sorry, ethanol. These are all hydrogen initially. What happens when making ethanol is that carbon, where I've just deleted the bonds, forms a double bond with oxygen. And that is now carboxylic acid. That's in fact ethanoic acid. So we write that as CH3COOH. But that part there looks like this. So that's a carboxylic acid. That's vinegar. This is specifically vinegar or ethanoic acid, which is a dilute acid. So carboxylic acids are chemicals with a functional group COOH. So look, there's the functional group. There's the functional group. There's the functional group. There's the functional group. Methanoic acid, COOH. HCOOH. Ethanoic acid, CH3, COOH. Propanoic acid, C2H5, COOH. Butanoic acid, C3H7, COOH. And that's what's shown here. So I'm going to show you how to draw one more. Let's look at propanoic acid. So you draw your 3 carbons. Now you draw your functional group for your ethanoic acid. So you go to the 3rd carbon and draw your double oxygen bond and your OH bond. Now that carbon has got 1, 2, 3, 4 bonds. So that carbon's done. Now you're looking at the other carbons and finishing the bonds off. So the carbon number 1 has got 3 more bonds available to react with hydrogen. And carbon number 2, the one in the middle, has 2 more bonds available. So we now have propanoic acid. Now carboxylic acid will react with a carbonate. Now, these are just reactions that we've done before. What happens when an acid reacts with a carbonate? It makes a salt, water, and carbon dioxide. What happens when acid reacts with alcohol? This is something new. It makes ester plus water. So what we've got here, we have a carboxylic acid group. And we've got our OH group from our alcohol. And, see, I'll show it here. So we've got a carboxylic acid group there. Now that's the carboxylic acid group. So this will be attached to whatever it's attached to, however many carbons. Over here, we've got our alcohol group. Now, this is a dehydration reaction, as in water is removed from it. So what will happen is this water part here gets removed. And that remaining part of the ethanol attaches there. What we've now got is an ester, because what we've attached is a carboxylic acid to an alcohol. I'm just showing you how the ester is made. You don't need to necessarily know how to make the ester yourself. You will need to be able to do this when you get to when you get to A levels though. So in chemistry, a pure substance is a single element or compound not mixed with any other substance. So if you only have something that only has one type of element inside it or only one type of compound, then we know it's pure. If it's got anything else inside it, then it's classed as a mixture. Now, we can tell the difference between a pure substance and a mixture because a pure substance has a sharp melting or boiling point. Because it's only one substance, it will only have one melting or boiling point. Whereas in a mixture, you have a range of melting or boiling points because you've got so many different things within it. So these 2 graphs in a question, you just need to know that when you've got a horizontal line, it shows one sharp melting boiling point. That shows a pure substance. You know it's a mixture when you have a range of melting and boiling points, when you don't have a sharp horizontal line. Okay, what is a pure substance? So in everyday language, a pure substance can mean a substance that has had nothing added to it. In other words, it's unadulterated and it's in its natural state. For example, milk. What is a formulation? Many products are complex mixtures in which each chemical has a particular purpose. So formulations are made by mixing the components in carefully measured quantities to ensure that the product has the required properties. So a formulation is a mixture that has been designed as a useful product. So here's examples of different formulations: fuel, alloys, paint, um, fertilizers, different types of food. Well, some of the chemicals that we add to food. Lots and lots of different types of medication are formulations. Okay, chromatography. Chromatography is a method that can be used to separate mixtures and give information to help identify a substance. So it separates usually mixtures of liquids. Now, the way chromatography sometimes is poorly understood, so we'll quickly go through this. Please ask lots of questions because chromatography is a common topic. Now, the piece of paper is a stationary phase, and the water, the solvent that is added to, now it doesn't mean it has to be water. Whatever the solvent is, whatever is added will be the mobile phase. Now, the different dissolved substances in a mixture are attracted to the two phases in different proportions. This causes them to move at different rates through the paper. So what will happen is the mobile phase will be absorbed by the paper, and as it rises through the paper, the inks that have been put on the pencil line will dissolve into the water and be taken through the stationary phase. Now, if they're more attached to the stationary phase, they won't rise as high. If they're more likely to dissolve in the mobile phase, they'll move higher up. So let's go through it one step at a time and some of the mistakes that people make. So step one is draw the origin line in pencil along the bottom of the paper. Now, we do this in pencil because pencil is insoluble. What some people do is they draw it in pen. If you were to do this, the origin line would move also because the ink will dissolve into the solvent and you won't know where your origin line is. Then you place dots on the test samples in on the paper. People don't usually make mistakes with this. Then you place the paper in the solvent with the origin line and the samples above the solvent. So if you look here, the solvent is below the paper line. Placing the samples below the solvent, this would cause everything to run in the water. So if you put the water line higher, that means all of this stuff will dissolve into the water and it'll go out of the paper into the water instead. If something's insoluble in water, then you have to use a different solvent. So some of these inks, some of these inks that have been added might not dissolve in water. So if that's the case, usually the experiment's done again using a different solvent, for example, ethanol. Okay, now how to collect results. Leave the chromatography paper to run until the solvent front is near the top of the paper. So what we're doing here is we're allowing the water to rise up until it reaches this line, till it reaches quite high up. And we call that the solvent front. Now you measure from the origin line up to the solvent front, and you measure from the origin line to the height, the middle of the ink spot to where it's risen up to. So that's how we can calculate the RF value. It's the ratio of the distance moved by the compound to the distance moved by the solvent. So when you're doing the distance moved by the compound, you measure. I know it's the arrow here says 8.4 and it's measured well above, but the measurement should have been up to the middle of that of the compound. So that's 8.4. Distance moved by substance. Distance moved by solvent will be from the origin line to the solvent front. Again, the arrow's slightly big. 12.2. Divide them and you got 0.69. Now the RF value should always be less than 1 because the compound can't is dissolving in the solvent to rise upwards, so it can't go beyond the solvent. Okay, so what do these results show? They shows that B is a pure substance. They show A is made of 2 different pigments. It shows B is pure because there's only one substance there. It shows that C is made of 3 substances. It shows that D is made of 2 substances or 2 pigments. Okay. Tests 8.2.1, test for hydrogen. How can you test for hydrogen? Again, this is a very common test that comes up every year. And what a lot of students do is they just write squeaky pop test. But if the question says describe how you can test for hydrogen, you can't just write squeaky pop test. So what you do is you take a burning splint to the mouth of the test tube, and if you hear a squeaky pop sound, then you know it's hydrogen. So you take the burning splint to the mouth of the test tube, and if it makes a squeaky pop sound, then you know it is hydrogen. How can you test for oxygen? So you insert a glowing splint. So a glowing splint is one that was burning, but now you've blown out the flame, so it still has embers. And when you insert it into the oxygen, it relights. So you insert a glowing splint, so the one that's got embers, into the test tube containing the gas. If it relights, it's oxygen. The test for carbon dioxide. Use an aqueous solution of calcium hydroxide, lime water. So calcium hydroxide looks like this. When carbon dioxide is bubbled through, it turns the lime water cloudy. So here you've got a colorless solution of lime water. When you add carbon dioxide to it, it becomes um, cloudy. Now, one thing I want you to keep in mind is why does it turn cloudy white? They haven't asked, I've not seen this question yet in this exam board syllabus, but it's something that came up in the Edexcel paper. So I'm just going to mention it to AQA students as well. They asked in the Edexcel paper, why does it turn cloudy white? And that's because when lime water, when you add to it carbon dioxide, it makes calcium carbonate as a precipitate. That calcium carbonate precipitate is white in color. So it makes a white solid called calcium carbonate. So just to keep just to keep it in mind. Doesn't necessarily mean it'll come in the AQA paper, but just in case. Okay, test for chlorine. How can you test for chlorine? Dip a litmus strip into the gas, and it should be damp litmus. And why does the litmus strip need to be damp? Does anyone know? So the reason it's damp is so that the chlorine gas can dissolve into the liquid. If you put a solid piece of paper, it's not going to react with the gas, or it's not going to pick up on the gas. So the damp litmus paper allows the gas to dissolve into the paper. So the damp litmus strip is added to the gas, and if it's chlorine, initially it turns red, and then it bleaches white if chlorine is present. Okay, now 8.3 onwards is triple only. So it's chemistry only. Now, with all of 8.3, and we'll look at some practice paper. We'll look at some practice questions towards the end. What I want everyone to pick up on and notice here is that as a topic, it needs to be memorized. If you memorize this inside out, the questions become really, really easy. So first thing is flame tests. And the whole point of topic 8.3 is how to identify metal and non-metal ions. In other words, how to identify unknown substances. So if you have an unknown substance, you can do lots of different tests. You can do flame tests. You can react it with certain chemicals, and you get different results. So you need to memorize all those different results so you can identify an unknown substance. So here, a test that involves, so here's the flame test. This is where you get um, a Bunsen burner and you burn the metal ion. And when you burn different metals, they turn to different colors. So for example, lithium gives a crimson red flame. Sodium gives a yellow flame. Potassium, a lilac flame. Calcium, an orangey red flame, and copper gives a green flame. So you can sometimes people can struggle to identify the difference between lithium and calcium, but regardless of that, we have to memorize this. If we're doing triple award, we have to memorize it. You need to know every single positive test. Now, what are the limitations with flame tests? If a sample contains a mixture of ions, that some of the flame colors can be masked. So it can be very difficult to identify them. This can happen if the nichrome wire was not cleaned between uses. Because the way you do this experiment is you take the nichrome wire, you dip it into the metal, then after you've done that, you actually dip the metal into acid. Now, why do you dip it into acid? Because the metal then reacts with the acid, and you can see the bubbles of gas being produced. When it stops reacting, there's no more bubbles of gas. Now, if you've got a strong uh, crimson red flame, so if you've got a mixture of metals like lithium with a strong crimson flame, and you've got potassium, which is and sodium, which is a yellow flame, then you might not see the sodium yellow flame because because the crimson red flame is a lot brighter than the yellow flame, the sodium flame. So that's one of the issues. The other issue is that if the nichrome wire is not cleaned properly between tests, then chemicals get passed on to the next test. Okay, so how can we identify metal ions using sodium hydroxide? So if you add a metal ion solution to a test tube, add sodium hydroxide, NaOH, and observe the color of the precipitate formed. Because what you're making now is a salt. Use the color to identify the metal ion. So aluminium makes a white precipitate, calcium makes a white precipitate, magnesium makes a white precipitate. That's not really very helpful, is it? You've got three that make a white precipitate, but you know it's aluminium because if you keep adding sodium hydroxide to it, eventually it dissolves completely. Now with calcium and magnesium, if you go to the flame test, calcium burns with an orangey red flame. Magnesium burns with a bright white light. So then after you've done this test, if you end up with calcium and magnesium, you can couple it up with the flame test and work out which one is which. Copper 2 makes a blue precipitate. And we should know that from copper 2 sulfate when we made salts or when you made salts in school. Iron 2 makes a green precipitate. Iron 3 makes a brown precipitate. So again, need to memorize this. So this is, as we just mentioned, this is a limitation. That you've got three things that all have a white precipitate. But we've explained how you can get past that. So we can continue to add sodium hydroxide in excess and the precipitate disappears. Then we know it's aluminium. However, if the precipitate does not disappear, we don't know if it's calcium or magnesium, so we can couple it up with a flame test. Now, how can we identify carbonates? When you burn a carbonate or you add a carbonate to an acid. So again, think back to now we're looking at non-metals now. We're looking at non-metal ions. So let's say you've got calcium carbonate and you've got calcium hydroxide and you've got calcium oxide and you're trying to identify which one of the three is a carbonate. So what you would do is add an acid. I should just write HCl. Let's add HCl to all of them. Now, the only one, when you react these different ones, that's going to make water. That's also going to make water and a salt. Here, we're going to make water, a salt, and also carbon dioxide. When that carbon dioxide bubbles through lime water, what happens to the lime water? It turns cloudy. And that shows that the original substance was a carbonate. So let's try a different one. Let's see, we're trying to identify if this is sodium carbonate. What do? We add it to the acid. If it is a carbonate, it releases carbon dioxide gas. When the carbon dioxide gas bubbles through the lime water, then what happens? It turns to a white color. And we know that the substance was a carbonate. It contains CO3 2 minus. Okay, how can we identify halides? Halides are from group 7, halogens. So F minus, Cl minus. Because we're talking about ions, not atoms. Bromine, bromide, Br minus, iodide, I minus. So what we can do here is add dilute nitric acid to the solution. So dilute nitric acid. So the first thing we're adding is HNO3. Then we're adding silver nitrate. And then you observe the color of the precipitate formed to identify the halide ion. Now, fluorine is too reactive, so fluorine is usually nothing happens with fluorine. So chloride gives a white precipitate, bromide gives a cream precipitate, and iodide gives us a yellow precipitate. So again, if we're trying to identify an unknown substance, one of the things we can do is add nitric acid, silver nitrate, and then if we get one of these three color changes, we know it's a chloride, a bromide, or an iodide. Now let's say it turns red. Then it means it wasn't any of these three. None of these experiments will turn red, by the way. I'm just giving a random example. So if it changes to a color that's not one of these three, then we know we've not seen Cl minus, Br minus, or I minus. So if you're trying to identify a non-metal ion or a metal ion, if you don't get a certain positive result, then you know that that particular ion is not involved. Okay, how do we identify sulfates? So a sulfate is SO4 2 minus. So you had hydrochloric acid, then you had barium chloride. If a white precipitate is made, then it contains a sulfate. So this table summarizes everything. If it's a carbonate, you add dilute acid and bubble through lime water. And if the lime water turns cloudy, then we know it contains a carbonate. Now, for a sulfate, if we add hydrochloric acid and barium chloride, then we get a white precipitate, and then we know it's a sulfate, which is SO4 2 minus. If we add dilute nitric acid and silver nitrate, If we get a white precipitate, then we know it's Cl minus. If it's a cream precipitate, then we know it's Br minus. If we get yellow precipitate, we know it's I minus. So how could we determine the ions present in this solution? So you could test for metal ion by taking a sample and adding sodium hydroxide. Or you can do a flame test. So there's our two tests linked to metal ions. So with sodium hydroxide, we had three different metals, for example, aluminium, magnesium, calcium, that turn white. Flame tests give us a range of colors as well, and then that helps us to identify our metal positive ion. Then we can test for negative ions, and that will take 3 samples because we can do one sample to test for carbonate, one sample will test for sulfate, and one sample will test for halide ions. So that solution is put through 5 tests. You add sodium hydroxide to it to find out if it's got a metal ion. You can do a flame test to it to check if it's a metal ion. Then you do 3 tests for carbonates, halides, and sulfates. So these 5 tests need to be memorized. And the outcomes, the positive results need to be memorized as well. So let's have a look at this question. My apologies, the answers are already there. So let's look at each compound. We've got compound X. From the flame test, there's no color. When we added sodium hydroxide solution, it became a green precipitate. Now, a green precipitate means it's Fe2+. And then when you add hydrochloric acid and barium chloride, it produced a white precipitate. That means it's got SO4 2-, and there's no reaction from nitric acid, so that means it's not a halide. So now we know it's FeSO4, iron sulfate. Next one, from the flame test, we got yellow flame. That means a yellow flame means it's Na plus sodium. No reaction, no reaction. Adding nitric acid and silver nitrate solution gave a yellow precipitate, which means it is iodide, I minus. So we know it's Na, sodium iodide. Then we've got flame test, no color, but adding it to sodium hydroxide solution gave a brown precipitate. That means it is, I'll do it here, Fe3+. Green means Fe2+, brown means Fe3+. Adding hydrochloric acid, barium chloride, no reaction, so it's not sulfate, but it gave a cream precipitate when nitric acid and silver nitrate were added. So that means it's bromide, it's Br minus. So that is FeBr3, iron bromide. Okay, a group of students had 4 different colorless solutions in beakers 1, 2, 3, and 4. Shown in the figure. Well, no figures are shown here. But this is a good 6-mark question. The students knew that the solutions were sodium chloride, sodium iodide, sodium carbonate, and potassium carbonate, but did not know which solution was in each beaker. Plan a method that could be used to identify each solution. So I'm not even going to read this. What you need to do to get full marks is write down, or you can do it one at a time. So it says plan a method that could be used. So you've got 5 different, you've got 2 different tests for metal positive ions, and you've got 3 different tests for non-metal positive negative ions. Non-metal negative ions. So you're essentially just going through each test and then adding your positives. So you'll say sodium. So you say I'll do a flame test to identify sodium and potassium. So what that does is it identifies which one is potassium carbonate, identifies which three are sodium. Then, in addition to that, you can add sodium hydroxide solution to it um, as an additional test. And then you can do your three non-metal tests. So you've got halogens, you've got chloride and iodide, which will give you distinct colors. And then you've also got two carbonates that will both make lime water turn white. Potassium carbonate will, in the flame test, will have one color. Sodium carbonate will have a different color. So it's just bringing all that information, all that knowledge together. So here, look, add each solution to a wire for a flame test. You can add silver nitrate to it. The solution that makes a white precipitate is sodium chloride. Add each solution to a wire for a flame test. Sodium will make a yellow flame, potassium lilac. So that or identifies potassium carbonate. Add nitric acid to each. Now the carbonates will bubble here, and then the carbonates. So if you add an acid to the carbonates, that will make carbon dioxide gas. That will make lime water go white. So this is not in that much detail, this particular answer. The solution that makes a yellow precipitate is sodium iodide. So I would go in way more detail than this. Learn those five inside out. Okay, instrumental analysis. So what is instrumental analysis? The use of equipment to carry out an analysis of chemicals and detect elements and compounds. So the advantages with instrumental analysis is that they're accurate, they're sensitive, and they're fast. So you know when we think back to flame tests, what's the main issue with the flame test? The main issue with the flame test is that um, it's all dependent upon a person's opinion. You look at it, you observe it, and you can make mistakes between different colors. Also, if there's multiple ions, the eye might be able to distinguish between one ion and the other from a color perspective. So using instrumental analysis, using technology makes it more accurate, sensitive, and it's a lot faster. So what is flame emission spectroscopy? The sample is put into a flame and the light given out is passed through a spectroscope. So again, it's burnt, but the light given out goes through a spectroscope, and the output is a line spectrum that can be analyzed to identify the metal ions in the solution and measure their concentrations. Now, this is something that we'll look at in a bit more detail when we do the pre-exam workshop, but I would advise having a look at some past paper practice questions. So let's say you've got the line spectrum for sodium, and it looks like this. And then you've got another one for lithium, and it looks like this. Let's add another one, and you've got potassium as well. And the potassium one looks like this. Now you have an unknown substance, and you do a use a spectroscope for it, and the unknown substance ends up looking like this. Then you can compare it to the other spectrums, line spectrums, and say, oh, that's the same as lithium. So the unknown substance was lithium. Or it could, if it looked like this, for example, then that's a mixture between lithium and sodium. So you say it's got lithium inside it and it's got sodium inside it. Now, the flame emission spectroscopy is an example of an instrumental method used to analyze metal ions in solutions. So it's a lot more accurate than not just a plain flame test. So Currently, Earth is made up of about 78% nitrogen, between 20 to 21% oxygen, and the gases like carbon dioxide, water vapor, noble gases, etc., are have small trace amounts. Carbon dioxide is the one that we do need to know. Well, we don't need to know, but we need to. It's good for us to know that's around 0.04%. So, what percent of the Earth's atmosphere today is oxygen? Around 20-21%. The percentage of argon in the Earth's atmosphere today is the same as it was in the Earth's early atmosphere. Suggest why? Because it's unreactive. Now, the percentage of oxygen in air is 21%. The mass of air in the classroom was 220 kilograms. Calculate the mass of oxygen in the classroom. So all you're doing here is 21%, so 21 divided by 100 times 220, and that equals 46.2 kilograms. Okay, Earth's early atmosphere. The best way to learn about the Earth's early atmosphere is if you learn it like a story and just think of it from a logical, rational perspective. There's some there's some elements to the story where you might have questions, as in where did this come from or where did that come from? But to do well in the exam, just learn it as a story. If it comes up as a 6-mark question, it's a nice and easy 6-mark question. So theories about how the Earth's atmosphere formed have evolved or changed over time. Evidence is limited because of scale, because we're talking 4.6 billion years and longer, which is the same issue with evolution. So here's one theory and one suggestion on how the Earth's atmosphere actually formed. So initially, we would have had one theory suggests that during the first billion years, there's lots of volcanic activity, meaning under the Earth, it would have been very volatile because of the sheer heat, which would have led to lots and lots of volcanic activity. If you've got lots and lots of magma, you've got lots of pressure under the crust, it has to be released somehow. And it was. And what was released then through the volcanic, through alongside the lava was ammonia, methane, nitrogen, carbon dioxide, and water vapor. Now, ammonia is NH3 and is important because it provides nitrogen as well. Methane is CH4. Nitrogen is N2. Carbon dioxide is CO2. And water vapor is H2O. Now, the nitrogen is unreactive and has built up over time. The nitrogen is unreactive because between two nitrogen atoms, you have a triple bond. And to break 3 covalent bonds, a triple bond is very, very difficult. One place this actually occurs is within cars. So this is why we have catalytic converters. So what happens with nitrogen is in around 2000 degrees, so either within the engine of a car or when lightning strikes, it actually breaks those bonds. So the nitrogen becomes free to react with oxygen. So that means it can become either NO or with the help of a catalytic converter, it can become NO2. Both are greenhouse gases, not greenhouse gases, sorry. They both can lead to acid rain. So how did the Earth's atmosphere actually form? So what we're saying is, initially we've got only these chemicals in the air. We've got ammonia, methane, nitrogen, carbon dioxide, water vapor, little or no oxygen. So when the Earth then started to cool down across this billion years, as soon as it went below 100 degrees, the water vapor condensed, meaning it formed clouds and it rained. So we had lots of precipitation and the oceans were formed. Now, if the oceans formed, you've now got lots and lots of water molecules on the Earth, and what those water molecules would have done is absorbed some of the carbon dioxide. Now, the carbon dioxide that dissolved in the oceans would have reacted with some of the things in the water to form carbonates. So carbonates in the water precipitate, making sediments. And what do sediments make? Under pressure, sediments make rocks. So the carbon therefore became locked in rocks. So for example, limestone is a type of rock that's calcium carbonate. In fact, if you look at the shells of lots of animals that live in the water as well, that's also calcium carbonate. Okay, so some quick questions. What gases were present in the Earth's early atmosphere after the oceans had formed? Carbon dioxide, ammonia, methane, nitrogen. There are many theories about how life was formed on Earth. Suggest one reason why there are not many. There are why there are many theories because there's not enough evidence and it was too long ago. Explain how the first seas formed. As soon as the temperature went below 100 degrees, the water condensed. It went from a gas to a liquid and then dropped to the earth to form the oceans. Now, during the first billion years of the Earth's existence, the amount of nitrogen in the atmosphere increased. Give one source of this nitrogen. Volcanoes. Suggest one reason why there was no liquid water on the Earth's surface billions of years ago. Because the Earth's temperature was too high. In other words, it was beyond water's boiling point. So the water was in a state of boiling. In other words, it was only able to exist as a gas. What was the main gas in Earth's early atmosphere? Millions of years ago, carbon dioxide. So the main gas in the air, other than, well, at this point, water has dropped into the oceans. And after that point, it would have been carbon dioxide. So in the early atmosphere, we would have had zero, none, or very little oxygen. But now we have about 20%, 21% of the Earth's atmosphere is now oxygen. Carbon dioxide was most of the atmosphere and now it's in trace amounts, around 0.04%. So when the amount of oxygen increased, animals began to evolve also. So what we've just said now is it was very, very, it was the Earth was a hot ball of magma. It released all this additional pressure through volcanoes. Volcanoes released all these different gases. As the Earth started to cool, the water condensed. When it went below 100 degrees, the water condensed. It dropped as precipitation, as rain. And some of the carbon dioxide got absorbed by the rain. Now, algae that lived in that water was able to use carbon dioxide because algae is green. It's a type of bacteria. It has chloroplasts. It used the sun's energy to photosynthesize. So it took in carbon dioxide and started to release oxygen. Alongside the algae, because there was so much carbon dioxide and there was plentiful water, plants started to evolve also. So initially, algae and plants evolved. They took the carbon dioxide out of the air, trapped it within themselves, and they released oxygen. So now the amount of oxygen increased, and that means oxygen breathing animals began to evolve. So we've just said volcanoes release gases, condensation of water, it dropped as rain. The rain absorbed lots of carbon dioxide. Because of that carbon dioxide in the water, algae photosynthesized, and generally because of the high proportion of carbon dioxide in the air, plants photosynthesized and evolved, and that meant they started to release oxygen. So carbon dioxide levels started decreasing, oxygen levels started to increase. And this is the equation, word equation and formula equation for photosynthesis. You just need to have a 6 here because it's 6 oxygens that were produced. So oxygen was produced by photosynthesis, and so its proportion increased within the atmosphere. And in theory, it's been 21% for the last 200 million years. So why did carbon dioxide decrease? One, the evolution of algae and plants. Two, some of it dissolved into the oceans and became locked in rocks. And three, because it's locked within animals and plants, when those animals and plants died over many years, that has those dead animals and plants have been converted into fossil fuels. So that carbon that was locked in animals and plants, trees, etc., has is been locked up in fossil fuels. So describe what happened to the carbon dioxide in the Earth's early atmosphere. So the carbon dioxide in the Earth's early atmosphere was used by plants for photosynthesis. It dissolved in oceans. And now, organisms that live in the water, for example, if you've got animals that live in the water that have got shells, a lot of those animals, what they're actually able to do is when they take in the carbon dioxide that's in the water, they can convert it into their shells. So the carbon dioxide dissolved in the oceans was used to make shells, marine organisms. Well, the shells of marine organisms. Some of it got locked up as limestone to make carbonates, and some of it got locked up in fossil fuels. So how did the formation of coal decrease the amount of carbon dioxide in the Earth's early atmosphere? So when you've got plants and trees that have died and been locked up under all these layers above it, that provides the amount of heat and pressure to convert that tree or dead plant into coal. So plants absorb the carbon dioxide. When the plants convert into coal, that means the coal has locked up that carbon. Okay, greenhouse gases. So greenhouse gases are gases that contribute towards climate change. So you've got carbon dioxide and methane, which are a concern because these molecules stay in the air for years or centuries, particularly carbon dioxide. And then you've got water vapor. Water vapor is actually a greenhouse gas, but it's not an issue because it only stays in the air for a few days. Now, what these gases do, the greenhouse effect, it traps some of the energy from the sun and keeps our planet at a suitable temperature for life. So we actually need the greenhouse effect. The carbon dioxide that's around the Earth, so that blue line which I'm just drawing there, when the sun's energy hits the Earth's surface, it initially, so when it comes to the Earth's surface, it comes as shorter wavelength radiation. And when it is absorbed, so the sun's energy, when it comes to the Earth, it comes as shorter wavelength radiation. For example, shorter wavelength is visible, well, sorry, yeah, visible, UV, X-ray, gamma. Usually it comes in the form of rays to some extent, although UV rays are absorbed by the ozone layer. So when the energy comes from the sun, it comes in shorter waves, and it can come as actually it can come as visible light too. That's absorbed. That visible light is absorbed by the Earth's surface. When it's reflected back, it's reflected as a longer wavelength. Now, longer wavelength are easier to be absorbed by greenhouse gases. So greenhouse gases absorb longer wavelength radiation. So if you've got a layer of carbon dioxide, so you've got a layer of carbon dioxide, the short wavelength will go through, but the long wavelength that comes back will be absorbed by it. Now, when carbon dioxide absorbs this long wavelength of electromagnetic wave, this long wavelength radiation, it absorbs it and it re-emits it in every single direction. What that means is this carbon dioxide layer here, the initial blue circle that I drew, sends some of the energy back towards the Earth. Now that's actually a positive thing because generally speaking, that increased the Earth's temperature by about 2 or 3 degrees, which has stopped a big chunk of the world not being in a mini ice age. Because if we didn't get that 2 or 3 degrees, a lot more of the world would be under ice. The issue, however, at the moment is the additional carbon dioxide that we're putting into the air. So human activities have increased the amount of carbon dioxide, the amount of methane in the air. So carbon dioxide has increased because of combustion, as in burning things in oxygen, specifically fuels. plus oxygen, because what do fuels and oxygen release? Carbon dioxide plus water. The water part's not too much of an issue, but the carbon dioxide part can linger for years to hundreds of years. And deforestation. We're cutting down so many trees um, because of our increase in agriculture. And that increase in agriculture and the cutting down of trees means we have got less trees providing us with oxygen and taking carbon dioxide out of the air. Then methane comes from waste and increased agriculture. So when we put our food waste and we compost it, what happens is microorganisms feed off that waste and they produce carbon dioxide gas as well. And also they produce methane. Now, methane can be burnt off and used, but we waste a lot of food now. So that wasted food has caused a massive increase in methane. Also, increased agriculture. A lot of the time when we do deforestation, it's to make new farms. A lot of those farms have got more cows and sheep, etc. And that increase in cows and sheep, sorry, have increased the amount of methane. So why is the theory of global warming widely accepted? The evidence to support the theory of global warming has been peer-reviewed. So peer review is when the science community evaluate the evidence of others. So one scientist does the experiment, then they pass that evidence in a journal to the science community, then other people in the science community do the same experiment. And by doing the same experiment, they show if their results were the same or different. And that prevents false claims. So it also ensures that scientists are confident with the accuracy of the data. However, global warming is and climate change are complex and difficult to model. So we have an understanding that global warming is happening. We have an understanding that we have an increase of carbon dioxide and methane in the atmosphere. So we understand that's going to have an impact on the amount of energy that comes back towards the earth. But to explain the overall impact of it is difficult. And this has caused models to have been simplified. And this has also meant that there's some uncertainty, and so not all people support the theory. Now, what is global warming? So global warming is the rise in global temperatures that can lead to global climate change. And we've seen this global climate change um, happen over the last few years. We've had hotter summers, we've had colder winters, we've had a lot more storms, lots of things are happening that didn't happen even if you go back 4, 5, 6 years ago. So these are the impacts. What we're about to go through now is the consequences of global climate change. So number one, polar ice caps melting. So organisms that live on the ice are losing their habitats. So organisms living on the ice are losing habitats because the ice is starting to melt. That causes a rise in sea levels. That increases flooding everywhere. And now the areas that have been flooded with seawater have saltier soil, so things don't grow as well. And that has a knock-on effect on the destruction of habitats. Now, if the sea levels are rising, that's one thing. If the sea becomes warmer, then automatically, if you warm something up, it has more energy, the particles move around more, it requires more space. So the increase in temperature also causes the sea levels to rise further. Now, we've probably seen this over the last few years. We've had an increase in extreme weather. So we've had more storms, more flooding, and all overall, what that's led to is a destruction of more habitats. So we've had flooding. If we look at it from a European perspective, we've had flooding in Spain, flooding in quite a few different countries. We've had flooding in England, um, and we've had more storms. We've had some major storms in, for example, America and certain parts of the world. It can also lead to changes in migration because birds move to places based on the weather, the temperature, etc. So organisms such as birds or insects may change migration patterns. They may migrate later, earlier, or they might migrate somewhere else. and that can disrupt the food chains. So in the UK, over the last few years, what we've noticed is there's certain birds that haven't been to the UK for many, many years have started to come back to the UK. And there's certain new birds that have started to come to the UK. For example, in one of my relatives' gardens, they've got a bird, not a bird nest, like a box version of a bird nest that any bird could enter if they wanted to. And they've actually got a bird in there that's sort of come all the way from Japan. So it's a bird that's native to Japan and it's laid its eggs in that little box. So you can see how birds are now migrating to some migration patterns have shifted. And also this ultimately might disrupts the food chain because some of those birds are eaten by certain carnivores, um, and then that has a disruption to the whole chain. Okay, it also leads to extinction. So different plants and animals will be at risk of extinction. For example, the turtle, because the turtle will lose nesting sites because of rising sea levels, and there's a risk that 30% of plants and animals will be at risk by 2050. Now, the other reason why turtles could become extinct is because warmer sand means that more of the turtles are born female. So not only are they losing their nesting sites because the water levels are rising, they're losing, majority of them are being born female. So that balance between male and female isn't there. Changes to rainfall. So some areas have now got heavier rainfall and become wetter. If it rains too much in an area, that can destroy habitats. And also, where this destroys habitats as more land will become desert. So this is more linked to if a place doesn't have as much rainfall, more land can become desert. And so some areas will have less rainfall and become drier. This is what I said before, seawater will expand. When water's warmed, it expands. For example, when making a cup of tea, put water into a pot, into a pan. If you make tea in a pan, I mean, or if you just put water in a pan generally for cooking pasta or anything, as you start to boil the water, the hotter it gets, the more it rises. Because the water particles inside are moving around faster, they need more space. And to get that additional space, they expand. So warmer water will mean that water will have a greater volume. That will lead to flooding and the destruction of habitats. Okay, carbon footprint. So, what is our carbon footprint and how can it be reduced? So, the total amount of carbon dioxide and other greenhouse gases emitted over the full life cycle of product, surface, or event. So, it's how much carbon dioxide a product, a service, or an event releases over its life cycle. So, for us, if we can look at our carbon footprint on a daily basis or a yearly basis, and we can see how much carbon dioxide overall, the net carbon dioxide are we releasing. So we'd have to work out how much carbon dioxide something produces and how much it takes in. So for example, if I own a forest and at the same time I own a car, I can calculate how much carbon dioxide is released through the petrol in the car and how much carbon dioxide do I take in because of the forest that I own or the trees that I've planted. So the carbon footprint can be reduced by reducing carbon dioxide and methane emissions. So how can we do that? We can use solar panels to make electricity. We could take a bike to school or to work instead of a car. And we can improve home insulation. Meaning we don't have to put our heating up on as high. Atmospheric pollutants. So the combustion of fuels is a major source of atmospheric pollutants. Most fuels, including coal, carbon, hydrogen, they contain some sulfur. So if you've got your lump of coal, now this is an allotrope of carbon, meaning it is made of carbon. But within there, you find some sulfur, parts per million. Now, when you burn this coal, it releases CO2 predominantly. But that sulfur, when you burn it, when it reacts with oxygen, it also releases a small amount of sulfur dioxide. Now, when sulfur dioxide mixes with rain, it turns to H2SO4, and therefore leading to acid rain. So the gases released into the atmosphere when we burn a fuel could include sulfur dioxide, carbon dioxide, which leads to global warming, carbon monoxide, which irreversibly binds to our red blood cells, stops them from carrying oxygen, so it's toxic. Carbon, which is soot, which can cause global dimming and respiratory issues. Sulfur dioxide, you can release nitrogen dioxide, which causes respiratory issues as well, which is also causes acid rain. So carbon dioxide is formed from complete combustion of fuels. Carbon monoxide, carbon particulates are both formed when there's due to incomplete combustion of fuels due to a lack of oxygen in the air. So it's incomplete combustion when there's a lack of oxygen. Then you've got sulfur dioxide, which I've just explained. You have things like coal that contain sulfur. So when you burn the coal, you also end up producing sulfur dioxide. And oxides of nitrogen, which I explained before as well. In the car's engine, you've got it's very hot and it's high pressure. And the nitrogen triple bond breaks either through lining or through the car's engine. And then the nitrogen, because that triple bond is broken, the nitrogen can react with oxygen to make nitrogen dioxide and nitrogen monoxide. Now, the issues with carbon dioxide is it causes global warming. Carbon monoxide is a toxic gas, so it reduces oxygen content in the blood. So if you have your red blood cell, inside there's no nucleus, instead you've got an iron molecule and which is attached to four protein groups, which we call hemoglobin. The whole thing's hemoglobin, and that attaches to oxygen usually. But in a situation where there's a fire and there's incomplete combustion, the carbon monoxide attaches instead. Now, if carbon monoxide attaches, although oxygen is released automatically whenever the cell goes past a respiring cell. So whenever the red blood cell passes by a cell that's not got much oxygen left, because it's respiring, for example, it passes the oxygen across. It naturally diffuses. Carbon monoxide just attaches irreversibly. So the only way to sort the problem is destroy that red blood cell and replace it with a new one, which isn't going to happen instantaneously, by which point a person can have suffocated. And it's not easily detected because it's colorless and odorless. Carbon particles lead to global dimming and respiratory issues for humans, breathing problems. Sulfur dioxide dissolves in water to form acid rain. That damages buildings, particularly those made of limestone. So statues made of limestone, it damages plants, um, as well as animals that live in water, such as ponds and lakes. And the reason for that is if that water is full of acid, the water will evaporate, but the acid won't. So every time it rains, it's going to the acid part will accumulate. And oxides of nitrogen dissolves in water to form acid rain. It can also cause respiratory issues, just like sulfur dioxide. Okay, so let's continue with where we left off in our physics. 6.3.1, infrared radiation. So what is a perfect black body? All organisms, all bodies, no matter their temperature, emit and absorb infrared radiation. So all bodies absorb and emit infrared radiation. So when we say something's a perfect black body, we mean an object that absorbs all the radiation that comes in contact with it. It does not reflect any of it or transmit any of that radiation. So in that respect, it's the best emitter. So it absorbs all the radiation and it emits all of the radiation. So you've got an object. Generally speaking, if you have any object, some energy will just be absorbed, some will bounce off, and sometimes things can transmit the energy as well. In this case, all the energy is absorbed. And once all of it's been absorbed, as in it absorbs absolutely everything, it means eventually it also will be a perfect emitter, so it emits everything as well. So here's a scenario. A body is at a constant temperature. This means the body is absorbing radiation at the same rate at which it is emitting radiation. Another scenario. So if a body stays at one temperature, it means the amount of heat energy leaving is the same as the amount of heat energy entering. If the temperature of a body is increasing, it means it's absorbing radiation faster than it emits. So if you've got an object that's increasing in temperature, it's got more energy that's being absorbed and less is being emitted. So what does the temperature on Earth depend on? The rates of absorption and emission of radiation. So that's one thing. So the rates of absorption, emission of radiation. So that means like we just did in chemistry, if you look at topic 9 in chemistry, you have long wavelengths. So you have radiation come from space that's a short wavelength. When it hits the surface of the Earth, it's absorbed, then it's re-emitted, but as a longer wavelength. And that longer wavelength is absorbed by carbon dioxide or methane, greenhouse gases, and then the greenhouse gas re-emits it in every single direction, with a lot of it being re-emitted back towards the Earth. And some energy will just hit the ozone layer and reflect back as well. So what has happened to the temperature of the Earth over the last 200 years in terms of radiation? The temperatures on Earth are increasing. This is because in the past, the radiation emitted into space was equal to the radiation absorbed from space. So before, the amount of energy entering the Earth was the same as the amount of energy leaving the Earth. But now, the temperature of the Earth is starting to increase. So what that means is today there's less emission into space, and so there's an overall net absorption of radiation. So now we're keeping more of that radiation in than we're releasing. So the overall temperature has now increased. Okay, and that takes us to the end of topic 6. So what do we use the Earth's resources for? We use it for warmth, shelter, food, transport. Natural resources supplemented by agriculture provide food, timber, clothing, and fuels. So these are some really important key terms. We need to know what a finite resource is. That's a resource that can only be used once and is in limited supply. Renewable, a resource that can be constantly replaced and will not run out. And sustainable. Development is meeting the needs of the current generation without compromising the ability of future generations to meet their needs. So sustainable development is something that's really important and needs to be considered when any actions are taken right now, so that future generations aren't impacted. So chemistry plays an important role in improving agricultural and industrial processes to provide new products and in a sustainable manner. Now, what is potable water? So potable water just means water that's safe to drink. Now, potable water contains low levels of dissolved salts and a few microbes. So that means it's not chemically pure because it contains dissolved minerals. Chemically pure would mean it contains H2O and nothing else. But the water that we drink has some minerals inside it. It has a little bit of calcium. It has some carbonates, etc. It's got some magnesium sometimes. It's got a few different things in there which are safe. We need those minerals within our body as well, so it's not really an issue. So what do we call water that's safe to drink? We call it potable. What's the difference between potable and pure? Pure means no dissolved substances. It only has that one substance. So it only has one element or one compound, and that's it. Potable means it's got some dissolved substances, so it's not pure, it's a mixture. And how do we obtain potable water? So salty water is the water from the sea, and it has lots of salt in it. Fresh water, and some countries are fortunate enough to have lots and lots of rivers and lakes, etc. They have water from the rivers, the lakes, or rain, and that's little or no salt. So how do you obtain potable water? You get the fresh water, for example, from the river or the lake or the stream. Now you pass it initially through a filter. So filtration is step one. And what that does, it takes out the larger bits of dirt, twigs, leaves, etc. Step two is left in a container. And it's just left there still. And what happens is this is called sedimentation. All the little sediment bits, as in all the little bits that were too small to get stopped by the filter, they drop to the bottom. So all the sediment drops to the bottom. Then the remaining water is filtered off, and then the germs that are within it, as in the microorganisms within it, are killed using either ozone, which is O3, so it's blasted with some O3. The O3 reacts with the microorganism that kills them. You can use UV light or chlorine. Usually we use chlorine because UV light is expensive, using ozone is expensive. You don't have to add much chlorine to kill off the bacteria and the viruses and the microorganisms. So how do you obtain potable water from a salty source? So we can remove salt from the water by heating it up and collecting the steam. So we can use distillation, or we can use the evaporation. We can also use a specific process called reverse osmosis, which is where you've got, for example, you've got lots of water molecules on this side, and you've got your partially permeable membrane, and less water molecules on this side. Naturally, generally speaking, water will go this way. But the reason you've got less water on this side is because you've got more salt particles. So this side's got salt particles and less water. But we want that water to be separate from the salt. So what happens is, almost like a plunger type device, forces the water through, leaving the salt behind. So this is reverse osmosis, as in it's going the opposite direction to osmosis, and for that reason it needs energy. And so this is expensive. It's an expensive process. Both are expensive because both need energy. So in fresh water, you filter it, do sedimentation, and then you blast it with some UV or ozone, or add chlorine to kill the germs. With salty water, you do distillation or reverse osmosis. Any impure water, you can just use distillation, heat it up. In some countries, they boil the water just to kill off the germs. Okay, so let's have a quick look at these questions. Describe how groundwater and seawater are treated to produce potable water. So groundwater and seawater are filtered and sterilized. And seawater is salty, so it's distilled or reverse osmosis is done. Now, if you look at this diagram here, it says the diagram shows a simple method for collecting clean water. This method is called solar distillation. Explain the process that occurs in this method, that occurs in the method shown in the diagram below to provide clean drinking water. So, the plastic sheet probably has a darker color, so it absorbs heat from the sun. So the water, and that means the water underneath the sheet in the can, just there, warms up. The water evaporates. It condenses. So, sorry. So the first thing is, see the dirty water here. That's the contaminated water. That's the water that evaporates. When it touches this sheet at the top, it drips inwards, it moves inwards, and it condenses and it drips into this can in the middle. Now, it is possible, this is from past paper, so it is possible to get questions where you've got to use the knowledge that you already have, but in a new way. Okay, so how can we determine if water is pure? So we take some water, weigh the empty evaporating basin, add some water, heat the water until it evaporates. So we've got an empty evaporating basin. It's now filled with water. This water evaporates off. Now what's left behind is a small amount of salt. So you weigh it again. So before it was 58.32 grams. And now we can see the mass has actually increased. So that means that water was not pure. Now, something we've covered previously to check if the water is pure is you can just boil it. Now, if it's pure, it will boil at 100 degrees. If it boils slightly above, then that means you will have a range of boiling points, and that would suggest this and it has impurities inside. So boiling it would do exactly the same thing, would get you the answer as well. Okay, what is in wastewater? So wastewater treatment. Cities and factories make a lot of dirty water that must be cleaned before it goes back into nature. So the dirty water from toilets and farms needs to have germs and waste removed. So factory waste water may also need harmful chemicals removed. So how is this water treated? The dirty water is first filtered to remove big bits like grit. Then the water settles, so the heavy stuff sinks. So again, you have almost like a sedimentation process. And what you get at the bottom is sludge. In other words, sludge usually is the waste product. So if we're talking about what comes out of our bathrooms, then that would be more like the feces part of things. And the effluent would be more the urine. So the light stuff stays at the top and the heavier stuff goes to the bottom. So the sludge is broken down. Now they leave the sludge because the water is filtered off. The sludge itself is put under anaerobic conditions. Now, under anaerobic conditions, the sludge is essentially broken down to fertilizer, and that can be sold off to farms, etc., to be used in their fields. The effluent is cleaned using air and bacteria. So again, air and bacteria will aerobically break it down and make it safe again. so that water can be used. But generally speaking, wastewater isn't used for drinking. So describe what the different parts of sewage are and how they are processed. So sludge, the solid material that sinks to the bottom during sedimentation. How is it processed? It's anaerobically digested. So bacteria and other decomposers will break it down without oxygen. Now the effluent, that's the liquid that remains at the top after sedimentation. That's biologically broken down by bacteria using oxygen. So that's aerobically digested. Now, so how do we treat effluent? We use aerobic biological treatment. How do we treat sewage, sludge? We use anaerobic digestion. Explain why it's more difficult to produce drinking water from wastewater than from the water in the lakes. And that's because to get wastewater clean enough to drink, there's more processes involved. It also contains more organic matter, as in dead things. And it contains more microbes and toxic chemicals. Because anything that's coming from our bathroom has more organic matter and it has more microbes. Anything that's coming from a power plant, from a chemical power plant, etc., has toxic chemicals inside it. Okay, alternative ways of extracting metals. So how can metals be created from low grade ores? So the Earth's supply of metal ore is running out. And because the Earth's supply of metal ore is running out, copper ores are becoming hard to find. So scientists have developed new ways to get copper from low grade ores. So that's phytoextraction and bioleaching. They're two of the ways. These methods help tradition. So this way, these methods avoid the need for mining, so ruining the landscape. So in phytoextraction, wherever the mining has happened previously, they plant they plant plants, and as the plant grows, it takes minerals out of the ground. Particularly, this area is heavy in copper. Um, so the copper goes into the plant. The plants are then collected and burned, leaving behind an ash that contains the metal compounds. The ash is dissolved in sulfuric acid that makes copper sulfate solution, and then that copper sulfate solution is used in electrolysis, as in it can be used as part of the electrolyte, and that copper then is used with electrolysis and purified. Alternatively, bioleaching can be used. Bioleaching uses bacteria to break down low-grade ores. So what the bacteria does is it releases a kind of like an enzyme onto the copper ore, and that creates a solution that contains copper ions. We call that a leachate or leachate. Now that solution, again, you can either do this, which is displaced with scrap metal, scrap iron. So what the leachate contains is copper ions. So if you've got scrap iron, the iron is more reactive than the copper, so it displaces the copper, and so you're left with copper. So copper can be taken out of the solution by using scrap iron in a displacement reaction. So what the leachate produces is something it can produce copper sulfate, and we know from phytoextraction it also produces copper sulfate. If you add the iron's more reactive, it displaces the copper. Okay, make sure you know this reaction just in case it comes up, because I've not seen a 6-mark question on alternative extracting metals, but it could come up. And if it's a 6-mark question, then you're going to need to put things like how displacement can be used to extract copper as part of your answer. The other thing you can do is electrolysis. Copper 2 plus ions. So when you add the copper sulfate, it splits into copper 2 plus and SO4 2 minus. And the copper 2 plus will go to from inside here, it'll be attracted to the negative cathode where it'll gain electrons. So it'll gain 2 electrons and become reduced. So pure copper is formed. Okay, next is life cycle assessment. Before we do that, what will actually happen is copper 2 plus will gain 2 electrons to become pure copper. In other words, it has gained electrons, so it's been reduced. So both of these processes can be used with bioleaching and phytoextraction. So just if you look at this as a potential 6-mark question, you need to learn what bioleaching is, what phytoextraction is, and then you need to know displacement with scrap iron and electrolysis to remove the copper as well. Okay, life cycle assessments. So in a life cycle assessment, LCAs or life cycle assessments check how products affect the environment at each stage. Usually these kind of questions are evaluative questions where you're given information and you couple that up with the knowledge that you already have to get your full marks. So at each step, when you're recycling, when you design the product, the resources, the production, packaging, transportation, distribution, the usage, the waste disposal, the life cycle assessment checks the product's effect on the environment at every single point. So what are the different parts of the life cycle assessment of a product to consider? So stages of a product's life cycle to consider are how getting and processing raw materials, making and packaging the product, using how the product will be used during lifetime. So all of these are key points. And disposable and how it can be disposed of at the end of its life. Transportation is another part, and distribution at each stage, because that's burning of fossil fuels to get from one place to another. So what are the limitations of life cycle assessments? Now we can measure the use of water, resources, energy, and some waste quite easily. However, giving numbers to pollution effects is harder and involves opinions. That means LCAs are not completely objective. So it means a company might actually produce a lot of pollution, but because it's based on opinions and is not completely objective, it means someone can leave saying, actually, it's not too bad. It's not producing in that much pollution. So what are the limitations of life cycle assessments? So some LCAs are shortened or selective to evaluate a product, but they can be misused. They might be designed to support pre-planned conclusions, such as making a product look better for advertising. So life cycle assessments do have limitations. Like I said, it's evaluative questions. So when you're going through past paper practice, this is another important topic just to have a look at. It doesn't come up often, which means it's something that you should look into just in case it does come up this year. So the reduction in use, reuse, and so reduction in use, or we can reuse things, or we can recycle. And recycling of materials by end users reduces the use of limited resources. Use of energy sources, waste, and environmental impacts. So if we reduce how much we use certain things, or we reuse or we recycle, that's better for the environment. So it means less energy is used, we're not wasting a resource, and it has less impact on the environment. So things like clay, ceramics, building materials, metals, glass, plastics, these are all produced from limited raw materials, as in the materials that eventually will run out. Much of the energy for the processes comes from limited resources. Obtaining raw materials from the earth by quarrying and mining causes environmental impact. So even to get these certain metals and things out of the earth, even to get crude oil to make plastics, these are require quarrying and mining. So these are having an impact on the environment as well. They have an impact on habitats and biodiversity. So how can we reduce our use of resources? So metals can be recycled by melting them down and reshaping them into new products. The amount of sorting needed for recycling depends on the material and the final product's required properties. For example, scrap steel can be added to iron in a blast furnace. This reduces the need to extract more iron from the iron ore. So with scrap steel, what happens is steel is just iron, but with other bits added to it. So when you put it into a blast furnace, all the other bits burn off, leaving just the iron behind. We can reuse things like glass bottles. Glass bottles can be crushed and melted to make different glass products. Other products cannot be reused and so are recycled for a different use. Okay. Um, okay, 10.3.1 corrosion and prevention. So the gradual corrosion is the gradual destruction of metals by reacting with oxygen and water. So corrosion is just when a metal reacts with an oxygen. So metal plus oxygen becomes metal oxide. Or it could be metal plus oxygen becomes metal oxide where it's just one oxygen, depending on what group it's in. So rusting is an example of corrosion, but that's corrosion that happens to iron. Now, for corrosion or for rust, which is a special type of corrosion to occur, iron, water, and oxygen need to be present because the oxygen dissolves into the water and the water is in contact with the metal, and then it makes it easier for the metal and the oxygen to react. So, how can corrosion be prevented? We can apply coats that act as a barrier, so we can add grease, we can paint it, we can electroplate it. That means covering it with a cheaper metal. Some coatings are reactive and contain a more reactive metal to provide sacrificial protection. For example, zinc is used to galvanize iron. So zinc is more reactive than iron, which means that only the zinc reacts with the oxygen. And how else can corrosion be prevented? So another thing is aluminium. Aluminium has an oxide coating that prevents it from further corrosion. So what that means is, if, for example, we had these are all aluminium atoms. Well, they're the internal ones. Yeah, so we have the outer aluminium ion atoms there. All this outer layer, when it reacts with oxygen, becomes aluminium oxide. Now, aluminium oxide is quite unreactive. And because it's unreactive, it becomes a protective layer. And it protects the all the aluminium atoms on the inside from further corrosion. So aluminium has an oxide coating that protects it. So everything I've just colored in red is aluminium oxide. So aluminium oxide is a protective layer. Unlike iron oxide, which when it reacts with oxygen, it starts to flake off. That doesn't happen with aluminium. Aluminium becomes a strong layer. Now, alloys as a useful material. So bronze is made of copper and tin. That's stronger than copper. Brass is made of copper and zinc. That's harder than copper, but still malleable. Gold, because pure metals are quite soft. They're easily shaped. When we alloy them, we make them much stronger. Because metals, just like any solid, they have a regular arrangement. The atoms are regularly arranged. What that means is the layers can slide over each other. When you alloy it, what you're actually doing is you're adding another element that disrupts the layers. And now that those layers are disrupted, what that means is if I push it from here, that disruption stops the atoms sliding over each other. If I push from here, it stops the atoms sliding over each other. So it gives that extra strength. So that's why with gold, even if someone says it's pure gold, they still add another metal to it just to add a bit more strength. So these are some examples of alloys. Now, steel is a stronger version of iron, alloys of iron with carbon and other metals. Now, when you put too much carbon, so steel is just carbon and iron. And that's your norm, your most common steel. Now, if it has too much carbon, it becomes really strong, but it's brittle. If it has a small amount of carbon, it's softer and it's easy to shape. Stainless steel is iron with chromium and nickel. That's hard and it does not resist, it does not rust, so it's rust proof. Aluminium alloys are really good for use in aircraft, drink cans, and cars because it's low density. Not particularly heavy, so it's perfect for an aircraft or a car as well. Ceramics and composites. So most of the glass we use in soda lime glass is made by heating a mixture of sand, sodium carbonate, and limestone. So borosilicate glass is made from sand and boron trioxide. It melts at higher temperatures than soda lime glass. So you have different types of glass. So most of the glass we use is soda lime glass, and that's quite fragile. But if you add boron trioxide to it, it makes it more heat resistant. Clay ceramics, that includes things like pottery and bricks. They're made by shaping wet clay and heating in a furnace. Now, what we've got here is um, low density polythene and high density polythene. So the properties of polymers, the properties of polymers depends on what monomers they are made from and the conditions under which they are made. So, just excuse me 1 second. So the kind of properties we're talking about, so the properties of polymers depend on what polymers they are made from and the conditions under which they're made. So the kind of properties we're talking about is, for example, how flexible they are, how strong they are, how heat resistant. Now, if the monomer, so if we here we've got two examples, we've got low density and high density polythene, but they both produce from ethene. Now, if the monomer that they're made from is a small molecule that joins with others to form, um, sorry, so depending on how they're made, so when you've got low density and high density, depending on how they're made, depending on the conditions, you get different uses from them. So, for example, um, low density polythene is made by using a high pressure, and you can use most different catalysts. But what you end up with is things that you would use in a carrier bag, for example. So you use low density polythene for carrier bags because as a plastic, the plastic is quite flexible and it's weak. Now, high density polythene it has more bonds between these layers. It's made at lower pressure, and there's a specific. It has needs a specific catalyst. You don't need to know about the catalyst element of this, but it ends up making a plastic which is more rigid. It's stronger. Is usually used um, in pipes, for example. Then you've got thermal-softening polymers. Thermal-softening polymers melt when they are heated. And the reason they melt easily is because there are no strong bonds between the chains. You have a few intermolecular bonds, but these bonds are easily broken. Now, with thermosetting polymers, they do not melt when they're heated because they've got strong covalent bonds between the chains. So these are less flexible. These will make something that's a solid plastic item. Now, composite. First thing we need to understand what a composite actually is. So a composite is a material made from two or more different materials combined together to get the properties of both. So it's what it says here. Material made up of two or more materials with different properties that are combined to make a material with improved properties. So what you end up with is you end up with a substance. A composite is a mixture of those multiple materials and you get the benefit from each one. Now, composites are made of two materials, a matrix or a binder. Now, the matrix is the main material that holds everything together. So you have to think of the matrix. It says binder there, which is a good word actually. It's something that binds everything together. So it's like the glue or the background material that holds everything together. It surrounds the other substances and it binds it in place. Then you've got your fibers or fragments. This surrounds and binds together fiber reinforcements. So we call the fibers and fragments, we call them reinforcements. So that should be in brackets. Fibers are the reinforcements. So these are the pieces or fibers that are added into the matrix. They're often strong or light, but what they do is they help improve the strength or toughness. So what the matrix does, it keeps them in one position and transfers force to them. So we've got some examples here. Now, fiberglass is a good example because the matrix is like a plastic resin and it's got glass fibers in. And then, so that material, the fiberglass, is used for like boat hulls, car bodies, things like that. Concrete, reinforced concrete, you've already got the concrete, well, you've got the cement. Cement itself is a composite. So yeah, so concrete is made up of, the matrix is cement and the fibers or the fragments are sand and gravel. Now, this is reinforced concrete, so they've actually put the metal within that as well, and that metal adds flexibility and strength. Okay, the Haber process. The Haber process is used to make ammonia, which is then used to produce nitrogen-based fertilizers. So there's your process. The raw materials for the Haber process, now it's important to know where the raw materials come from. They are nitrogen and hydrogen. And the hydrogen comes from natural gas, and the nitrogen is taken from the air. Now, what happens is the gases, so you've got nitrogen, it's added to hydrogen to make two ammonia molecules. So the gases are passed over. Again, you need to know over here, we know where the hydrogens come from, we know where nitrogens come from. Here, we need to keep in mind that there's a iron catalyst. It's got a high temperature, 450 degrees, high pressure of about 200 degrees. Now, whatever doesn't react here is recycled. So the remaining hydrogen and nitrogen are recycled. Now, and a coolant goes through this because when the ammonia cools, it turns into a liquid. and it's removed. So it allows the process to keep continuing. Because this is linked to Le Chatelier's principles, apologies, this arrow is wrong. It should be a reversible arrow. Because it's linked to Le Chatelier's principles, if you reduce the concentration of the product, you keep. So if you reduce the ammonia, which way does the equilibrium shift? It shifts to the right. It shifts in the direction of the product. So you make more of the product. And because they keep recycling the hydrogen, nitrogen, what does that do? That it keeps increasing the concentration of reactants. So if you increase the reactants, you also make more product. They also have a compressor, so that increases the pressure. In other words, again, that pushes it in the direction of the products. So the Haber process, some of the hydrogen and nitrogen react to make ammonia. The reaction is reversible, so some ammonia breaks back down into nitrogen and hydrogen. But that's why they're cooling it down, because the cooling down element of it removes the ammonia. So it keeps the forward reaction going. Okay, so the condition of the Haber process. The breakdown of ammonia is an endothermic reaction. So that means the forward reaction is endothermic, the backward reaction is exo. So a higher temperature would increase the amount of ammonia. However, at lower temperatures, the particles move slower. Sorry, let me start again. I've said this the wrong way around. Let me just rub that out. The forward reaction is exothermic. The backward reaction is endothermic. So this particular reaction prefers a lower temperature, because a lower temperature takes the reaction in the exothermic direction. However, the problem, if the temperature is too low, the particles will move slower, leading to fewer collisions between hydrogen and nitrogen, and so less ammonia would form. So a temperature of 450 degrees is a compromise, and it's used as an optimum. So it's not too high a temperature, and it's not too low. Now 200 atmospheres, because you've got, let's write the reaction out again. We've got nitrogen plus 3H2 becomes 2NH3. It means the forward reaction prefers higher pressure, because you've got 4 molecules on the left-hand side, 2 on the right-hand side. So increase in atmosphere or increase in pressure pushes everything towards the product. So the greater the pressure, the higher the yield of ammonia, as equilibrium is moved to the right. However, high pressure equals higher costs. So they use a compromise pressure of 200 atmospheres. Now, generally speaking, when reactants combine, so for example, you have carbon plus oxygen makes carbon dioxide. Usually, these kind of reactions, or if you've got HCl plus NaOH, which is a neutralization reaction, makes sodium chloride and water. These kind of reactions are all exothermic. So usually when things combine, it is exothermic. When things decompose, as in one thing breaks apart to become two, they're usually endothermic. But there are still some reactions where two things combine and it's endothermic. But in an exam question, they will tell you if it's exo or endo. And the last thing that's added is the iron catalyst. So why is the iron catalyst added? So iron catalyst, it lowers the activation energy of the reaction, is relatively cheap and it helps to achieve an acceptable yield of ammonia in an acceptable time. So all it does, a catalyst helps get to helps reach the equilibrium, dynamic equilibrium faster. So it speeds up the reaction for a relatively cheap amount of money without becoming part of the reaction. So this slide for those, well, this is really important to memorize. Okay, NPK fertilizers. So nitrogen, phosphorus, and potassium, all three are needed to help make plants grow better and increase crop production. Now, NPK fertilizers have all three of these important elements. So if it's an NPK fertilizer, it has all three. So NPK fertilizers are made in industry using different raw materials in several connected steps. So they are mixtures of different salts containing the right amount of nitrogen, phosphorus, and potassium. So it means the fertilizer contains salts that have nitrogen-based salts, phosphorus-based salts, and potassium-based salts. So how are they made? Ammonia is used to make ammonium salts. Nitric acid is used to make nitrate salts. Because ammonium is NO3, NH3, so it can be used. It can react, for example, with potassium. So here specifically ammonia reacts with certain acids to make an ammonium salt. So that releases the NH3, or it can react with nitric acid to make a nitrate. And again, that releases the, not NH3, so it releases nitrogen. And how are different components of NPK fertilizer produced? So potassium chloride, potassium sulfate, and phosphate rock are mined from the ground. So these are salts that would be added to the fertilizer. Potassium chloride, potassium sulfate, and phosphate rocks are mined from the ground, and they would then provide the potassium and the phosphate. So the ammonium, because ammonium salt is NH4 plus with something attached to it. Nitric acid, when it reacts with something, makes a nitrate. So it makes something NO3. So if this is part of the fertilizer, that provides the nitrogen. Whereas the potassium chloride or the potassium sulfate salt or the phosphate rock provides the potassium and the phosphate. The phosphate rock cannot be used directly as a fertilizer. So it's treated with nitric acid, sulfuric acid first. So it becomes a salt that contains the nitric acid, a nitrate or a sulfate group added to it. And that can make a soluble salt that can be then used as a fertilizer because it dissolves in the rain and it separates. Okay, so nitric acid, when nitric acid is added to a phosphate rock, it makes phosphoric acid. When sulfuric acid is added to a phosphate rock, it makes a superphosphate, which is calcium phosphate and calcium sulfate. And when phosphate rock is added to phosphoric acid, it makes triple superphosphate, which is calcium phosphate. So you don't need to know the reaction per se. You need to just know that how can you make the phosphate available within the NPK fertilizer. Again, when some of the questions that are asked on this topic, they are evaluative type questions. So it is important to have that practice, and the more practice papers you do, the better. Now, specifically, if you just give me 1 second. So when it comes to the whole NPK fertilizer topic, you need to know the following. Compounds of nitrogen, phosphorus, and potassium are used as fertilizers to improve agricultural productivity, which we've covered. NPK fertilizers contain compounds of all three elements. We've covered that. Industrial production of NPK fertilizers can be achieved using a variety of raw materials in several integrated processes. You don't need to know the process, you just need to know the fact. NPK fertilizers are formulations of various salts. So the actual fertilizer is made up of salts. Ammonia can be used to manufacture ammonium salts and nitric acid. So that's within there. Potassium chloride, potassium sulfate, phosphate rock, they come from mining. But whereas the potassium chloride and potassium sulfate can go straight into the fertilizer, the phosphate rock has to be treated with nitric acid or sulfuric acid, so it makes a soluble salt, which is what we've covered on this slide here. Now, students should be able to recall the names of the salts produced when phosphate rock is treated with nitric acid, sulfuric acid, and phosphoric acid. So you need to know the names of the salts that are made, and you need to be able to compare the industrial production of fertilizers with lab preparations of the same compounds given appropriate information. So what that means is in a question, you'll be given information and you'll have to break that information down with everything you know from your chemistry. So again, it's lots of past paper practice that's needed. Okay, thank you everyone. That is the end of chemistry. That's the end of paper 2 chemistry. Okay, so we're going to continue from where we left off yesterday. This is topic 7. So topic 7.3.2, uses of the generator effect. So the generator effect is used in an alternator to generate AC and a dynamo to generate DC. So AC is alternating current, so that's current that flows in two different directions, and DC, that's current that only flows in one direction. So if we've understood what we went through yesterday, it makes this whole topic a lot easier. So here what we're saying is the coil moves through the magnetic field and the coil cuts the magnetic field lines. A potential difference is induced across the coil. That means it's a complete circuit, so a current is induced in the coil. So every half turn, the potential difference reverses direction. So every half turn, the current changes direction too. So let's explain that in a bit more detail. So firstly, let's look at, so what we're looking at is how can we generate alternating current? So we can generate alternating current using a rotating coil in a magnetic field like a generator. So what we've got here is a rotating coil. Let me just highlight it in yellow. This is our rotating coil. So that rotating coil can be attached to anything that spins, that's causing it to spin. And as long as it's spinning, it's causing that coil to spin. So let's go through it one step at a time. The coil rotates in a magnetic field. So the coil is spinning between two oppositely charged magnetic poles. So we've got a magnetic field, and really quickly, when we did Fleming's left-hand rule, we mentioned F, B, I. F being the force. Now, right now, do we have a force? Yes, because the coil is spinning. So the force, this half of the one half of the coil, the blue half of the coil is moving, has a force pushing it upwards, and the red half has of the coil has a force pulling it downwards. So we've got our force. Do we have our magnetic flux density? Yes, we've got a magnetic field. Do we have current? If we have these two, then we're automatically producing a current. And that's what this is saying, we're generating a current. In this case, it's alternating. So the coil's spinning, and it's spinning in between the magnetic fields. As it turns, the coil cuts through the magnetic field lines. That's electromagnetic induction. So, because the coil is moving through the magnetic field, a potential difference is induced across the coil. Now, if you've got a complete circuit, which we do, we've got a complete circuit here. In other words, it's connected to, for example, a light bulb, as it is here. The induced voltage, because what does the voltage do? It pushes the electrons. It causes, and what is current is the flow of electrons. So this voltage that's being produced within that circuit is pushing the electrons along. So now we have current. Now every half turn, the direction of the movement changes. So look, if we look at Fleming's left-hand rule, if you look at the blue half, the thumb is pointing upwards. The magnetic field is going from left to right. That means the current is flowing out of the screen towards us. Now, so that means the current is flowing. So on the blue half, the current is flowing towards us. In other words, that way. Now on the red half, the thumb should be pointing downwards. Our first finger, the magnetism, is still flowing left to right. So that means our second finger is pointing inwards towards the screen. So that means the current is flowing this way. So that means the current that's formed, that's produced, is being produced in both directions. So after every half turn, each side of the coil is now moving the opposite direction through the magnetic field. This means the induced potential difference reverses. So you see that the blue half there, at the moment, it's here. Afterwards, it's because it's spinning, it's going to be on the other side. So when it was on the right hand side, the current was flowing this way. When it's on the left hand side, moving upward, when it was moving upwards, the current was flowing this way. When it was starting to move, when it spins around and it starts to move downwards, the current flows that way. So every half turn, we're inducing a potential difference. We're creating current. So because we're reversing the potential difference, we're pushing the electrons in one direction, and then it's pushing the direction in the opposite direction. So the current also reverses. So this constant reversing of direction every half turn means the current is alternating. That's why we call it alternating current. So let's quickly summarize it. The coil spins in the magnetic field. What does that do? It cuts the magnetic field lines. The voltage is induced. That makes the current flow. Every half turn, the direction of the voltage, the potential difference changes. And the result of that is we have an alternating current that's produced. So now let's understand direct current. So now in a dynamo, it has a split ring commutator. So this is something you need to know from a triple perspective. Okay, not so much, well, not at all from combined because it's not a combined topic. And it changes the coil's connection every half turn. So as the induced potential difference is about to change direction, so it's still spinning. In this case, it's spinning this way around now. So where we were saying, so just 1 second. So where we're saying, for example, the current flows that way, then it flows this way. What happens here is the split ring commutator changes the coil connections every half a turn. So you see how here you've got a negative and that's positive. Well, it changes it just as this is spinning, just as it about is now at that point it's going upwards. So the current is flowing this way. just before it starts moving downwards and the current starts flowing this direction, what the split ring commutator does is it changes the plus and the minus. So this side becomes plus, that side becomes minus. So now it means when the current flows, it continues flowing in that same direction. So as the induced potential difference is about to change direction, the connections are reversed. This means that the current that's produced inside it, this means that the current to the external circuit always flows in the same direction. Okay, so let's just quickly understand that. So now in a generator, we know we can produce alternating current. That's what that was in the previous slide. That should say direct current. Now in a dynamo, we still use exactly the same principle, but we use the split ring commutator to change the coil's connections every half turn. So let's go through this step by step. The coil spins inside the magnetic field. So same as you would in alternating current. As it spins, the coil cuts through the magnetic field lines, and that induces a potential difference across the coil. The current is induced. In other words, it causes current to flow. So now we've got current flowing through this coil. And it's part of a complete circuit, so the lamp will turn on. Now, naturally, as the coil turns, the direction of movement changes every half turn. So the voltage, induced voltage reverses every turn, just like in a generator. But what the difference is this split ring commutator. It switches the connection of the coil every half turn. So just as the voltage is about to reverse direction, the ring flips the connection. The commutator flips. So it goes from being plus minus and it flips. It goes to being plus minus to plus. And because it does that, it means the current keeps flowing in the same direction. So even though the coil's voltage is reversing, the split ring commutator flips the wires at the same time. So the current in the external circuit always flows in the same direction. Okay, so how do microphones work? Now, it would have made more sense to have the speakers and the microphones next to each other, but it's fine. Microphones is a triple only topic, which is why they've been separated. So microphones use the generator effect to convert the pressure variations in sound waves into variations in current into current in electrical circuits. So let's go through this. Microphones use the generator effect to convert sound waves into electrical signals. So let's understand this one step at a time. Sound waves reach the microphone. Now, a sound wave is a vibration in the air. So in the microphone, it hits a thin sheet called a diaphragm. So the air particles are hitting this thin sheet and causing it to vibrate. Now the diaphragm is very sensitive. It vibrates in response to the sound waves. The louder the sound, the bigger the vibration. So the diaphragm will vibrate a lot. And if it vibrates really fast, that shows that it's a high-pitched sound. Now the diaphragm is attached to a coil of wire. And so if it's attached to a coil of wire, what's that diaphragm going to do to that wire? It's going to cause that wire to move. Now, every time that coil moves back and this coil of wire moves back and forth, that coil of wire is in a magnetic field. So every time it moves back and forth, what does that do? It generates a current. So the coil is placed between the poles of permanent magnets. So when the wire moves through the magnetic fields, and as the coil moves, it cuts through the magnetic field. So now the generator effect happens. The movement of the coil in the magnetic field induces a voltage, a potential difference. So we're inducing a potential difference. And what does a potential difference lead to? Current. So in other words, we've now produced a current. So this induced voltage causes a varying current. And it's a varying current because this wire moves back and forth. For example, at points where no one's speaking into the microphone, you're going to have no movement in the wire, no potential difference, no current. When someone's speaking really loud, you're going to have current where the electrons are moving more. When someone's speaking with a high, singing or speaking with a high pitch, it's going to have current where the electrons are moving faster. So the current can then be sent to an amplifier, a speaker, or a recording device. Because the induced current is an electrical version of the sound wave. So now all it's doing is carrying that energy. And that energy can then be sent to a speaker, and the speaker then converts that into a sound. So let's just quickly recap that. The sound wave hits the diaphragm. The diaphragm vibrates. The diaphragm is attached to a coil that's within a magnetic field. And whenever that coil moves back and forth, it creates a potential difference, which creates a current, and it has a varying current. And when that varying current reaches the speakers convert it into sound. Okay, does that make sense? Good. If you want to give me a thumbs up if it makes sense, I'd appreciate it. Excellent, thank you. I know that whole topic 7 is a little bit tricky, but you've done really well. Excellent. Okay, transformers. What are transformers? So here we have our primary coil, and we have a secondary coil here wound onto an iron core. Now, iron is used because it's easily magnetized. So when electricity current flows through these wires, it induces magnetism within the iron core, which then creates an electron current in the secondary coil. So here on this side, you can see you've got less wires, and here you've got more. So this is a way of increasing the voltage. So the ratio of potential difference across the primary and secondary coils of a transformer depends on the ratio of the number of turns on each coil. So an alternating current in the primary coil produces a changing magnetic field in the core. This produces an alternating potential difference across the secondary coil. And so essentially what I just said, the current flowing through this wire creates a magnetic field in the core, which creates a potential difference in the secondary coil, which has more wires, and that the potential difference then creates a current. And because there's more wires, you're creating more current or more potential difference. So in a step-up transformer, the voltage of the secondary coil is bigger than the voltage of the primary coil. Because in a step-up transformer like this one, you are trying to increase the voltage. Because at higher voltage, the electrical power travels faster, and it also is more efficient. When current is too high, the more energy is lost. Now in a step-down transformer, the secondary voltage is less than the primary voltage. Now, if transformers were 100% efficient, the electrical power output would equal the electrical power input. So, power equals IV. So the power output of the secondary coil and the power input and output is measured in watts. The power input of the primary coil. So if we do I times V, we get the power of the secondary and the power of the primary, and they will always equal each other because power is conserved.